Yan. So, hello everyone. Can you hear me?
Yes.
Okay. Thank you, Sir Bob. Ayan. So, before we officially start, you may introduce yourself using our Zoom chat box. You may state your name, the institution, organization, or school that you came from, and please answer also our question. What convinced you to join the QNLP lecture series of the One Quantum Philippines? Okay. So, yeah, to officially start our lecture series. So, uh, let me introduce myself first. I'm John Vincent Sibonga. Currently, I am the operations and engagement team lead of the One Quantum Philippines, and I will be your host for tonight. So, yeah, welcome to the QNLP lecture series, the introduction to quantum natural language processing, brought to you by One Quantum Philippines in partnership with the DOST ASTI Project Itanong, QCS Project, UP Tacloban, DICT Region 8, UP Interactive Society, and Dev 8 Community. Okay, so before we start, so let's have overview of our session norms. So first is engage actively, immerse yourself in this learning experience, and be open. Let's have meaningful conversations with each other, and also always ask away. So if there's something that you want to clarify, if you have some question in mind, so please raise your questions. Don't be afraid to ask when you need to. And then lastly is respect everyone. So let's give each other our undivided attention full throughout the lecture series. Okay, so just to break the ice, so we want to know lang, no, how are you today? So press 1 if yeah, happy that that you survived the week, especially that there's a lot of you know things that happened this past few days from the typhoon and yeah and everything. And then two, if yeah, a little bit of chill, relax. And three, if you are super excited for our for our lecture today. Okay, yeah, I see a lot of uh, okay, a lot of trees and yeah, a lot of trees. There are some twos and ones as well. Yeah. So yeah, we are happy to hear that you're excited for our lecture series today. For the day one of our lecture series today. And yeah, we are really grateful that you decided to spend your weekend with us here in One Quantum Philippines. Okay. Okay, so first, let me introduce first who we are, the One Quantum Philippines. So the Quantum Computing Society of the Philippines, or the One Quantum Philippines, is a community-driven organization dedicated to advancing quantum computing in the Philippines. So one of our main goal is to help the Philippines make a transition from traditional computing to into quantum computing, and we envision a quantum enabled Philippines. Also, one of our goal is to promote the quantum computing education, starting from starting from the grassroots. That's why we are continuously initiating this kind of programs and events like the lecture series. So as of now, this is our third installment of lecture series. Before we had the lecture series with the Bulacan State University, and now with the UP Tacloban. And then okay, so here are our social media platforms. So if you want to keep updated with our latest events, programs, or just you just want to have some news regarding the latest quantum technology news here in the Philippines, so you may follow us on Facebook at facebook.com/1quantumph, And also in our Instagram, instagram.com/qcsp.ph. And also we have our um, LinkedIn account, One Quantum Philippines in LinkedIn. Okay, and also you may also visit our website, so onequantum.ph. So there's also information and updates regarding our programs, latest course offerings and such in our website. Okay, hi, thank you, Javes. So yeah, congrats and welcome to the QNLP lecture series. So congratulations for being one of the 450 plus registrants for this lecture series. Okay, and yeah, we are looking forward to have you in all of our sessions. Okay, so first for welcoming remarks, so may I call on Mr. Bobby Corpus, the president of QCSP and a board member of the OSTPCIEERD Quantum Technology Board. Hello, Sir Bob.
Hi, can you hear me?
Yes po, Sir Bob.
Okay. So thank you everyone for joining the UP Tacloban lecture series on Introduction to Quantum Natural Language Processing. We at QCSP are honored to present this in collaboration with UP Tacloban, DOST, DOST Advanced Science and Technology Institute, the Department of Information and Communications Region 8, Dev 8, and UP Interactive Society. So quantum computing is a fascinating subject. It's a paradigm shift, a completely different way of doing things compared to what we usually know in our daily computing lives. However, it is pivotal to the future of technology. So through this series, which extends over several Saturdays, we aim to provide you with a taste of the subject. So after the first part, there will be a modified hackathon or Olympiad, if you call it, for our pre-selected participants. And then the second part will build on top of the quantum computing knowledge that you already have to discuss the classical and quantum natural language processing. And so we strongly urge everyone to do the exercises because that's the only way, to really understand the subject. And collaboration is key. So try to team up with your fellow participants over Discord server, discuss solutions, and enhance your learning experience. For the hackathon participants, so you will be competing with other schools in solving as many challenges as you can on building quantum circuits. So best of luck, and here's to a fulfilling journey of learning. And I'll now hand over to John. Thank you, John.
Yeah, thank you, Sir Bobby, for the welcoming remarks. Okay, so and also may I call on Mr. Elmer Peramo for a special message, the project lead of the Itanong project and a senior science research specialist at the OSTS. Hello, Sir Elmer.
I think I remember Elmer said he will give a recorded message. Javis, did you get that message?
Oh, not yet po. Baka habol na lang po siya later.
Oh, okay.
Yes.
Sige.
Okay, hi. Thanks, Javes. Okay, so okay, let's move forward. So another special message from Dr. John Paul Yu Xiong, Systems Administrator at UP Tacloban, Chairperson of the Division of Natural Sciences and Mathematics at UP Tacloban as well. Hello, Dr. JP.
Yes, good afternoon to everyone. Hello, can I be heard?
Good afternoon. Yes po. We can hear
Okay.
you clearly.
Okay, so on behalf of the University of the Philippines Tacloban College, I welcome you to the Quantum Natural Language Processing lecture series, especially to its first lecture session. This event is a significant milestone for UP Tacloban as it not only strengthens our partnerships with leading innovators in this field like the One Quantum Philippines and DOST ASTI. But this partnership highlights our commitment to academic excellence and research innovation. We are honored to collaborate with One Quantum Philippines, DOST ASTI, DICT8, Dev8, and the UP Interactive Society because we recognize the immense potential quantum computing holds, especially in its applications to natural language processing. By bringing this initiative to Eastern Visayas, we ensure that our region is not left behind, but is part of this transformative journey. This lecture series offers a unique opportunity for students, educators, and the local ICT community to gain first-hand insights into this cutting-edge field, preparing us for future technological advancements. I hope you will complete this lecture series and earn a certificate of completion symbolizing your commitment to lifelong learning. Once again, I extend my heartfelt thanks to each one of you for your participation. I am confident that this event will be both productive and inspiring for all of us. Welcome, and let's make the most out of this opportunity. Thank you so much.
Okay. Thank you, Dr. JP. And on behalf of One Quantum Philippines, we would like to thank you also for joining us in this initiative to bring quantum education and quantum technology closer to the people. Okay. So for before we move to the lecture proper, so here are some reminders. Okay. Hello, Jabez.
Hello. Hi everyone. I'm Jabez. Ayan, mamaya na lang ako papakilala. Pero yeah, there's some reminders. You've heard from through email sa amin, di ba? And yeah, there's some reminders. First one is the participant handbook. Ayan, it's like a Google G Docs. All relevant information about the course or the program is on there. It was sent via email and available rin siya sa resources site natin. So, GDocs yung sinend namin since there might be changes or parang new updates para naman para hindi ma-outdate kung PDF lang, di ba? So, ayan, speaking of resources site, next slide please. Ayan, we've put up a site. No, it's qcsp-qnlp.notion.site and ilagay niya lang yun sa inyong browser. And all of the lecture recordings, homeworks, and resources will be on there instead of an LMS like Google Class or whatever. No, para at least isahan na lang, very simple. Nandyan lahat ng kailangan natin. And yan. So, next slide. So, this is how what it would look like for every week. Ayan, for example, day 1, September 7, the recording and homework, ayan, nandyan, supplementary materials would also be there within 24 hours. So, yeah, please be a bit more patient since maliit lang ang team namin. So, we do quite take some time to get back to you. And then, if you miss a meeting, and as mentioned sa email that you received, now you would have the chance to catch up. We know everyone's busy, lalo na Saturday to, we go out and as such. So the recordings would be uploaded naman. The forums would open on the day of the lecture and would stay open until the end of the program. So pwede mong speedrun. Speedrun mo ang program. Pero yeah, we encourage everyone to join as well pa rin, no, para makapagtanong kayo and makapag side to side kapag may coding exercises na tayo, no, may problem kayong nakita, mas mabilis, di ba, kapag live sessions talaga. The homework as well would be posted there and would be open up until the end of the program, no, para kapag medyo nahihirapan ka, no, need mo pang extra time to understand the lessons, no. Ayan. So we want you guys to succeed, no. Ayaw namin magbigay ng 1 week deadline. Tapos, syempre, kung hindi mo nasagot yan, parang maano ka. Anyways, I'm digressing. Sa next slide, please. Yeah, for program timeline, we will have a total of 12 weeks. Now that's from September 7, which is today, hanggang November 23. So that's 11 Saturdays. So syempre skip natin yung November 1 na holiday. So that's 11 Saturdays. Regular na 4 to 7 p.m. ang ating lectures via Zoom. So itong link na ginamit natin would be used throughout the program. So thank you po, UP Tacloban, for providing kahit na 1,000 tayo dito, kasya tayo dito. And we will have dedicated lab sessions. Mas maganda kung maka-join kayo, especially sa lab sessions natin para talaga we can have breakout rooms doon, tapos we can have mentors, no, para mas easy mag-debug kapag nagpo-program tayo. And we will also have special events, for example, the in-person hackathon, no, for participants bandang Tacloban. Ayan, so kung interested kayo, look out, we will send or we'll give more information about this in the future. And other events that would be for all. No, medyo exclusive po Tacloban lang. By the way, at first, it's limited to the Tacloban or parang Eastern Visayas region, pero we said na for our mission to share quantum education, di ba? At least man lang yung lecture series can be shared to everyone, and then i-host yung hackathon sa Tacloban. So next. Ayan, thank you sa mga nagsisend ng ano. Yan. There's information about the e-certificate requirements. Thank you po. Ayan, sa pag-send. You can check out their link doon. Lecture topics. Ayan, so day 1 would be the kick-off, which is today, and we'll introduce you to quantum already. Ayan. We will introduce you to the fascinating world of quantum. And then day 2, balik tayo sa math, fundamental math. Day 3 would be essential programming skills. And then days 4 to 6, balik ulit tayo sa quantum, no? And day 7, hackathon sa mga in-person, and then lab day naman sa mga hindi makakapag-attend ng hackathon. Day 8, ito na, i-apply na natin yung NLP, classical. And then day 9, we sprinkle quantum doon para maging na siyang quantum NLP. Day 10 would be a lab day for every one of us. And day 11 would be the program culmination. Most likely, if may special event. Now, we're still arranging it, so please bear with us. Pero if ever man, dun siya ma-hold. So more information would be on your handbook. Next slide. Ayan. Yeah, I think that's it. Giving back the floor to Vince. Thank you.
Okay. Thanks, Javes. So before we move to the lecture, so let's have some energy check first. So yeah, currently, what's your energy level? Is it 1, like a bit sleepy, or 2, very interested, and 3, if you are highly motivated. There's a lot of 2s and 3s. Yeah. Okay. Yeah. Okay. Thanks everyone for answering the energy check. And yeah, I see that there's a lot of people who are interested and really motivated for this lecture series. And yeah, we are very happy that you joined the QNLP lecture series. But additional information before we move to the lecture. So here in our Zoom meeting, we have the Q&A section. So if you have questions that or some clarifications or concerns, so you can use the Q&A section of the Zoom meeting, and at the end of the lecture, we will answer all of your questions and concerns. Okay. Thank you, everyone. So now, moving to the lecture proper. So first, let me introduce to you our first lecturer. So he is currently pursuing a PhD in electrical engineering at Chung-Yuan Christian University in Taiwan, where he also a recipient of the CYCU International Student Scholarship and the National Science and Technology Scholarship. He holds a master's degree in computer science and information engineering from Chonghua University and bachelor's degree in computer engineering from Adamson University here in the Philippines. Currently, he is the Chief Innovation Officer at Work Technologies. He leads the development of new products and manages research initiatives. And he also contributes to academia as a part-time associate professor at De La Salle University, Manila, Technological Institute of the Philippines, and other institutions, guiding students in research areas like quantum computing and computer vision. So, okay. Hello po, Sir Dylan.
Yes, hi. Can you hear me?
Yes po, loud
Great,
and
great.
clear.
So yeah, I think just a bit of announcement first. I think Sir Burns, the second speaker, would not be able to join us. So I will be filling up on his behalf. So yeah, I might be extending my initial talk, extending a bit of Sir Burns's coverage. So hi everyone, nice to meet you. I see some familiar names in here. So hi. Also, students here, I'm glad you have the fervor to attend this new type of this emerging technology talk. Forgive me though, I might turn off my camera for the rest of my presentation because I do have some intermittent, network issues right now. But yeah, I'll keep you if you have any questions, feel free to post them down in the chat box and I'll be glad to answer them later. So yes, allow me to share my screen and I'll just turn off my camera for a moment now. I'll turn it on once we're back in the Q&A. All right, so can you see my screen now?
Yes po, Sir Dylan.
Great, amazing. So yeah, welcome. So I'll be introducing you to quantum computing. So we are going to talk about a lot of things. What is quantum computing? Why do you even need to do quantum computing? Can we even do quantum computing in the Philippines? And actually, you can do it at your own home, especially if you have a PC. That's only the requirement. And are we ready for this? Of course, you are ready because you're here. So let's just have a bit of an outline. So again, we're going to talk about quantum computing, but there's actually a bigger picture to this. It's actually quantum information science and quantum information science and technology. We call it KIST as well. So it spans a lot of aspects here. It's not just with physics, not just with computer science, not just with IT. It spans a lot of fields considering, its applications. And we're going to get to that later on. And we're going to tell you, how do you really get started? And if you're a researcher, you're a student, you're finding out where could you actually use quantum computing, we're going to talk about that later. We can see some applications in the industry, agriculture, so on and so forth, even in finance. We can see some applications of quantum computing. So without further ado, let's start talking about quantum. So introducing our quantum technology. So if you are familiar with the economic observations, so some call it Moore's law, and Moore's law is the observation that you're cramming transistors into IC chips twice every time and it doubles every year. This is actually already demystified and broken for the past 5 years like that. And it's not actually two, it's actually exponential times 10 already. And that's amazing because we can put a lot of transistors that's computing power into a smaller space. But there is a problem to this. There is a limit on how many transistors that you can cram into a single area, because we want them to be smaller. These transistors become nanometers, even smaller than, thinner than your hair, or thinner than, a lot of things. And that's going to be a problem, because what if we scale down all of those transistors into near the size of electrons? So how could we handle those kinds of computations then? And what are the challenges? What would be the consequences if we have very, very small circuits, electronic circuits? Okay. So there is, IBM has announced its 2 nanometer chip. It's actually 3 years ago. Probably we have something new. But the thing is, if we have a 2 nanometer chip, okay, that's still significantly large. But remember, if an electron is a zillionth of that chip, we're still safe. However, if we pursue something even smaller, okay, we can expect some spooky observations in the quantum realm. As we go smaller, if you remember watching Ant-Man, if you become very small, you can go into a quantum realm. That is not entirely wrong. However, just in the terms of humans, we can't shrink ourselves. However, if we can shrink things into a very, very, very small size of an electron that is entering actually a quantum space or a quantum realm, as we, could call it. And that is amazing. However, it's also, we can also feel some drawbacks there. So if those who are, so took some quantum physics before, if you have heard of it, there is what we call quantum tunneling. So quantum tunneling happens is that when you have a wall, okay, a very thin wall, an electron could actually, could bounce, as we expect. If you throw a ball into a wall, towards a wall, it will bounce back, right? And that's expected. However, in the quantum realm, if you have a quantum ball in there and you throw it against a quantum wall, there is some probability that that ball could pass through walls, okay? And it would not bounce back. There is that probability. And what happens if an electron suddenly pass through an insulator, okay? That means the electron is now moving into a different circuit. That could mean a lot of things. It could mean that there is insufficient electrical flow to activate a transistor so that we can have 0 and 1s. That 0 did not become a 1, or that 1 did not become a 0. Okay, or it goes into another switch that suddenly opens, and that is a big problem when you try to compute. So one small computational error in a very, very complex computation scheme might ruin a whole, a lot of things. So that single decimal point could actually mean probably losses to a lot of people. That millisecond could be could turn to some seconds. That million could be a billion, in some cases. So that error in computing might propagate if we have those errors, and that's a problem if we have a very, very, very small electronic circuit in that case, right? Okay, so we need to be very careful. So how do we deal with that? So one way is we can't scale it anymore, so we just buy more computers. But if we buy more computers, we're consuming a lot more electricity. And that does not help in our global, in our global warming condition. We're now just increasing electricity consumption. And that's going to be very, very crucial. The increased carbon emission as well. So how could we deal with that? How could we deal if we are going to work with this kind of problem? So if you can't beat them, you can't beat quantum tunneling because that's a law of nature. Join them. So that is one inspiration in doing a quantum computer. So if you know Richard Feynman, if you watch the Big Bang Theories, he's a physicist, and he's one of the first people who had the idea, if there is a computer, a machine that could naturally simulate quantum mechanics, that is the best computer out there, because the world as we see it is quantum. The reason why you're hearing me right now, why you are seeing this slide right now, is because of quantum technology, because of quantum mechanics. Because you can feel, you can actually get some X-rays, that's actually because of quantum physics. The reason why you are seeing LCDs or have LEDs, that is because of quantum mechanics. So we are, living in a quantum world already. We're benefiting from quantum mechanics. Now, if very nature, you can actually simulate very nature itself in a computer, you are naturally computing something, right? So imagine naturally computing chemical bonds, okay, combinations of compounds, RNA folding, those natural stuff. Those are very hard to simulate in high performance computers, even, and they would take some time, and that takes a lot of electricity. But those are actually quantum mechanical process. Why they actually happen, right? That's chemistry, and chemistry is based on your spin electrons and how do you bond that. And that is naturally occurring in quantum physics. So if you have a machine that simulates that like water, that's amazing. That means you can simulate nature in its very core. And that's where you can look at quantum computers. Now, where does that fit into actual computing? Data could actually be inscribed into quantum mechanical objects. Say, for example, electrons, photons, ions. You can inscribe information in them, process them, and it could hold more information. And we can see that later on. So in the simpler sense, quantum computing or a quantum computer differs from a regular computer. We call that a classical computer that it applies quantum mechanical concepts. So you apply quantum mechanics to data to perform logic and formulate algorithms based on quantum mechanical processes. Okay. So the one big advantage for the tech people out there is that the development of quantum algorithm assumes parallel computing, right? So when you already design quantum algorithms, there is inherent parallel computing. You don't have to set up multiple CPUs, multiple cores, program every thread, because that is already inside the algorithm. It is implicitly there. All right. You don't have to explicitly code all of those things, but that is just the nature of quantum computing. So how do we do that? You use quantum mechanical concepts. So there is the term quantum bit. How do we prepare bits instead of 1 and 0? How do we make them quantum? There is the concept of superposition, and there is entanglement. Now, these are the very basic, the fundamental quantum mechanical concepts that we use for basic quantum computing. Now, there are more, and that's going to be discussed in the future lecture series, but we're going to just touch the surface of things with quantum computing. So let me just tell this, that a quantum computer will not replace all computers out there. Okay, it will not replace your gaming PC. It will not replace your MacBook. A quantum computer is a very specific computer that is good for specific problems, similar to how GPUs are very good in graphics processing. Okay, quantum computers will not run Microsoft Word. It will not run Chrome. It will not run Zoom. A quantum computer is specifically good for specific tasks. Okay, it's not a general processing unit. Okay, so let me just clear with that. It's not going to replace any type of computer in the future. Ideally, it could, but it's not practical in terms of the operational sense. And we'll get to that later. Why can't we? Why should not we do it? Okay, so we can, but it's not practical. So let me just tell you that there are variational improvements when using a quantum computer. So a quantum computer is good for specific problems. What problems are those? Say, for example, you have the RSA encryption. RSA encryption is considered NP hard as well. It's a factoring problem. And when you use a classical computer, a regular computer, and you try to crack a certain password, it might take around several million of years. For example, one password for one specific password. However, if you use a quantum computer, you have a chance that you can solve it in probably 17, 15 minutes instead, right? So that is a significant advantage. And specifically, we're going to use Shor's algorithm for that. Okay. There's another case where there is a somewhat better improvement. This is in unsorted database searching. So for those who have studied complexity, so if you do unsorted database search, it's like you're finding the name of a person in a yellow page, if you still know what a yellow page is, or rather you're trying to find a person's name in a whole spreadsheet. Okay, well, let's say a 100-line spreadsheet. Okay, and you don't know who that person is, but you know the person is, but you don't know what is their primary key, right? You don't have an identifier. They're just randomly out there. It's like for example, a data lake. You're finding something there. So if you run that case, the worst case scenario is you get, if you have 100 items there, you take 100 times before you can find that specific thing in the worst case scenario. So that complexity is n. That's O of n, right? However, if you are going to use a quantum algorithm, specifically called Grover's algorithm, it has a complexity of square root of n. So that means instead of having a worst case scenario of 100, okay,
Anong
you
ginamit?
are going to you only need square root of 10, square root of 100, which is 10. So just 10 iterations to find out where is the answer. Okay, that's Grover's algorithm. And there is what we call uncertain or highly variational speed advantage in quantum that applies, for example, adiabatic computing or AQC. And this is an example for optimization problems. For example, the traveling salesman problem. So the traveling salesman problem could be efficiently solved by classical computers, regular computers, if it's significantly small, okay, a small sample, number of houses or nodes. However, if you increase that value or increase the number of houses, the problem scales. Okay, it could be linear, it could be exponential, depending on your problem. However, a quantum computer would have expected it would plateau, and depending on the problem size. Okay, so that means if you have, for example, 100 nodes, and that could have a very large complexity. However, a quantum computer might have significantly lower than that, but it's only a sweet spot after a certain break-even point. Okay, so that's variation. So we can look at this how, quantum computers does not have it does have a very specific application. It's something it's good at. It's good for very large problems, okay, but not for very simplistic tasks. Okay, so 1 plus 1, it could work, but a classical computer could actually solve 1 plus 1 faster, right? So I hope you're aware with that. So it's not a general processing computer that would replace all computers out there. No. And there are a lot of quantum computers out there, different types. There's different quantum computing devices. So for example, there are quantum annealers and analog quantum computers that are just like the idealization of Richard Feynman. It's a computer that simulates nature at its very core, okay? For example, a quantum annealer is specific for optimization problems that tries to mimic quantum annealing processes, okay, and tries to solve good, values in what we call a binary optimization or 1 0 integer problem. An analog computer simulates nature itself, right? You can do quantum chemistry, material science, optimization problems. That is by nature of quantum computing. However, there is the goal of everyone, which is a universal quantum computer. It's idealized like a quantum Turing machine. So we would like to have this because in this case, we have error correction. We have better computational values. We can use it for quantum machine learning, quantum searching. It can be used for communication. Okay, that is the idealized quantum computer. And we're building this right now. IBM is one of the leaders in doing a universal quantum computer. However, another note is that there is no specific technology yet in how to do a quantum computer. It means, when I say no specific technology, there are a lot of efforts in how to make a quantum computer. There's no one way in creating a quantum computer right now. There's no standard yet. So it can be using superconducting qubits. So superconducting, that means if you prepare a qubit, like for example, an electron, you need to cool it near 0 Kelvin, around 3 to 5 millikelvin. And imagine that's very cold, okay? And we want that to happen because if we have a very cold place or very cold configuration, an electron would most likely, will not be moving. It's stationary. And once an electron, imagine that, that marble type of electron, it's not vibrating. And you can now easily control that using other methods. Now, there are other ways, such as trapped ions, silicon quantum dots, diamond vacancies, and V centers. We do have a lot of those. And that's not the focus of this talk and my talk. But again, there are a lot of ways to prepare this, and the different companies are doing different things. IBM is doing superconducting. Intel is using silicon quantum dots. Microsoft is using topological qubits, and so on and so forth. There are so many, so many being done right now. So we need to wait for a few more years so that we can see which one is a standard. But again, all of these are trying to achieve the idealized universal quantum computer. So what's the challenge? It's what we call coherence and fidelity, and we're going to talk about that later. So I'm gonna give you an idea first about information representation. Let's try to move let's have a paradigm shift from classical computing, the regular computing that you're doing right now, into quantum computing. In information representation, the basic unit of information is a bit, right? While in quantum computing, the basic information unit is a qubit or a quantum bit. Okay. A main difference is a classical bit is only 0 or 1 in one point in time. It's either on or off. It could not be both. But imagine a quantum bit is probabilistic by nature. It's what we call a p-bit. So a probabilistic bit, in theory, would be if you have 1 and 0, you have a switch, right? You can put the switch in between. That means it could be 50% 0, 50% 1, 70% 0, or 30% 1. So you can represent them both at the same time in some sort of probability or linear combination of those. So that's the same thing. It's realized by a quantum bit. Now, how does that happen? How does that? It's not on and off. Okay. So let's move this idea that a classical bit is represented by a number, a binary number. However, a quantum bit is represented by a vector. Vector, right? A vector. It's just like, one of those parts of a matrix in linear algebra. It's represented as that, not just a 1 or a 0. Now, how do I say that? So here, you don't find the math yet. However, when you represent a qubit, it's represented by a vector. And that could be represented in 3 dimensions, x, y, and z. And mind you that this x, y, and z is in the complex space, or what we call the Hilbert space. So you can represent a lot of things by just one qubit. That's a lot of information already to unpack. And the value that we're trying to get here, the zeros or ones, are what we call states, right? The information state. In a quantum computer, in quantum computing, we call this as a state vector because it's a vector representing the state of information of a qubit. Okay. So there is some math that it represents that idea, and that's here. I'm not going to explain too much on that. I'm just going to do an overview. But imagine that this is your configuration. So if you have what we call basis states, we have state 0 and state 1, or ket 0 and ket 1. The first part here is 1, 0. If you have a vector that's 1, 0, it's pointing upwards. That's an arrow pointing up. While 0, 1 here, or state 1, is pointing down. Okay, we're going to see that later. So again, when we look at a classical bit, it's either 0 or 1 at the same time because that's that's voltage switching, right? It's either activated or not. That's 0 volts, 5 volts, okay? There's nothing in between. So because if you remember, for those who have studied some electronics before, you need to surpass the activation voltage of certain silicon, of certain electronic components. That's usually 0.7 volts, right? So that's the case here. So what is the activation voltage? So it's only 0 and 1. It's not activated or not. It's activated or not. That's the only thing. However, a quantum computer goes beyond that. Okay. So again, we represent them as state vectors. Okay. And these state vectors, if you look at this, the ket 0 and ket 1, these cosines and sines are actually amplitudes. These are the amplitudes of measuring whether it's 0 or 1. It's pointed to the direction of 0 or pointed to the direction of 1. Okay. So these are amplitudes. And later, we can consider these as the probability of seeing or observing, measuring 0 or 1, or even both at the same time. Okay. So again, these A and Bs represent amplitudes. How strong do we see that? So if these are just amplitudes, right? These are A and B. These are actually just linear combinations, and there are another set of vectors. Okay. And imagine this. This A and B are amplitudes. In quantum physics, we can take this idea further, that these amplitudes could be represented as probabilities by just squaring them. So the probability of measuring or seeing 0 is A squared. And the probability of seeing 1 or ket 1 is B squared. So in total, this is going to be just like your regular probability equations. A squared plus B squared should equal to 1. That's 100%. Okay, that's the rule. That's actually Born's rule. So say, for example, if I have a qubit right here and it's pointing upwards, A is 1, B is 0. That is your 1, 0. That is your ket 0 state, right here. So just pull up my... Anyway, so the probability of this, so that's going to be A squared. So A squared here, 1 squared is 1, and that is 100%. So we have a 100% chance of measuring 0. Cool. Trivial. So if we have something now pointing downwards, so the amplitude of A, or the amplitude of ket 0 is 0, and the amplitude of ket 1, or the state 1, is 1. If we have the amplitude of 1, which is B, and we square it, becomes 1. That means we have 100% of measuring 1. So that's it. Very simple. It's just pointing numbers, right? Up and down. How about what happens if we point left and right? That's something next. That's called superposition. Okay. So if we can point upwards or downwards, we have a choice to point it sideways or all around, right? So we can't do that in classical, but we can do it in quantum. But that idea has a mathematical implication. That's what we call superposition. So a superposition of states or a superposition of values, that means it exists both states at the same time by a certain degree or a certain probability. So instead of being 0, either 0 or 1 at the same time, it could be 0 and 1 at the same time by a certain degree. So in this case, it could be 50% 0 and 50% 1. Cool, right? So how do we do it? How do we do with that mathematically? So if something is pointing sideways, okay, if you look at this sideways, this happens that if you're A, okay, if you're the amplitude of A here is 1 over square root of 2, and B is 1 over square root of 2. Let's say that's how we solve it. So if we do that, what is the probability of A? So if we square A, that is 1 squared over the square of square root of 2. So that is 1/2. So that means the probability of measuring ket 0 or being 0 is 50%. And that means if B is also 1 over square root of 2 and we square that, that's another 1/2. So that's another 50%. So that means it's a 50% probability of also measuring 1. So we look at that here, they have equal probabilities. And this is not just a mathematics, this is something observed in real life. And this is, again, superposition. So it goes back to that, the thought experiment provided by Erwin Schrödinger, wherein we have the cat in a box. Unless you open it, we don't know if it's alive or dead. While it's in the box, it is in a superposition of life and death. However, once you open it, the observation of the state, it collapses. When we say collapse, that doesn't mean they die. Collapsing in the quantum realm means it turns into in classical data. So in this case, the classical data is the probability measured in this case. Okay, so it collapses later on. Okay, so I hope you get that idea. So that is superposition. That is the first fundamental concept that we have in quantum computing that we can't do in classical computing, because you can't represent 1 over square root of 2 or the 0, 50% of 0 and 50% of 1, right? So how do we prepare an actual qubit, okay, before we proceed in having, multiple values? So a qubit actually is not, it's not electrical flow, okay? It's an actual quantum object. When you say it's a quantum object, it could be an electron, it could be a photon, it could be ions, those tiny things. So imagine inscribing information into those tiny things, those subatomic particles. Okay, there's can also be neutral atoms, right? So you imagine inscribing information to that. And remember, the information is inscribed by the orientation or the state vector of that object. Okay, it's not about the flow, it's about the actual object. So when you prepare those things, there's a lot of ways. One of them is trying to cool them down to near 0 Kelvin and to stabilize them so that they won't move. So say, for example, it's an electron. So an electron is steady. Okay, if it's steady, you can now have the power to control it using other means. Now, in experimental quantum physics, you can actually control them through using radio frequencies, sometimes with microwaves, or sometimes with lasers. Okay, you can try to cool them with lasers and try to rotate them the way you want them. Now, if you rotate them, that means you are inducing the state vector to turn around where you want it to be. So that's the same thing as controlling what is the value of a qubit. Same thing as going 0 and 1, turning the switch on and off. Okay, so that's preparation and stabilization, then a control signal. Once you have that, there would be, of course, a corresponding state vector, because once you turn the qubit around, there is changing state vectors. Okay, and you do an operation that lets it flip around, turn around 360, turn around 180 in X, Y, or Z. And that is how we can do operations, and that now induces some value. And that value is represented by a state vector, okay? Or sometimes you call it a quantum mechanical wave function, okay? So, okay, question here that I'd like to answer because it's really relevant on the slide. In what quantum property is the information encoded? Is it the spin or some other property? It's actually the spin. So we are trying to control the spin of, in some cases, in this case, electrons, right? So in other cases, those are other ways. So for example, in ions, that is a different thing. It's not about the spins now, but rather it steps into oscillations. Okay, so those are different things. But yeah, that's not the scope of this talk. I think some other speaker would be covering that. It's actually cool. If you want to go to the quantum physics side, I think that will be more in the quantum hardware, but here we're talking about quantum computing, but also very relevant though, because the computing properties could be affected by the hardware, the capabilities rather. So once you have your state vector, okay, you can now measure that and let it collapse into the classical value. So once you have the classical value, you can now read it out using electronic probes. And that will now be the values that would be interpreted by your classical computer, right? So you can now you can now have an interface, a low-level language, an assembly language that would be able to control this qubit. And we do have a stack for that. There's actually quantum assembly language, we call it QASM. That means you can now code directly to a quantum computer since it's now outputting classical values as well. Cool, right? So let's have an example. This is not electrons, but using an ion. So using an ion in ion trapping, you have these ions right here, okay? These calcium ions. And you can now prepare them also in a very cool way. Now you can control the universal and local spins of your electrons in this case, okay? So you can do it in many ways. One of them would be you can do laser beam pumping or cooling, or yeah. So another way is you control it using the microwaves or radio frequency electrodes. So when you apply an operation, let's say you want to flip the bit or you want to do some additions, or rather not additions, you do some multiplications, okay? You can do an operation and that will be sent to these lasers and microwaves, and that will induce rotations, okay? They'll affect the spin of an electron. And once you have that, you can read it out using these DC, direct current electrodes. It now measures the energy potential or the voltages that corresponds to the probability or the collapsed wave function. Okay. And that would now be the value that you're going to manipulate, or the value that's going to be deployed or displayed rather. So that's one way, okay, that we are going to work with your qubits. Hold on a bit. There's just a bit of a problem here. Anyway, okay, cool. Okay, why can't I move my slide? Give me a sec, guys. What's happening? Okay. All right. So yeah, okay, I can move it now. All right, cool. So that's just one qubit. What now? We actually have a lot of qubits right now, roughly around the thousands. And what does that mean if you have more qubits? So similar to the classical computing, if you have bits, you can form words. Okay, so 4 bits form a nibble, 8 bits form a word, and 16 bits you can get your hexadecimal ready, right? So the same thing here. However, there is a bit of a hitch here. Instead of a one is to one correspondence, if you have 3 bits, you have 3 bits that could be any combination of 0 and 1. Those are all the possible combinations, just 0 and 1. So just three possible representation at max. However, if you have 3 qubits, you have 2 raised to n, or rather 2 raised to 3 representations. All of the possible combinations of those would exist, right? So if you have 3 qubits, that's 8. If you have 2 qubits, that's 4. You have 1 qubit, that's 2. But if you have 4 qubits, that's 16. So there is a 2 raised to n progression. So if I have 5 bits, that's just 5 bits. But if I have 2 raised to 5 bits, that's a lot, right? What more if I have 10? That's already 1024 representations. That means 1024, classical values that you can parallelize at the same time. Instead of having 1024 bits, actually. It's just 5 qubits, rather 10 qubits, right? And you can do a lot with 10 qubits, mind you. So here, that's a very good advantage already. But how do we see that as the one with up and downs of the circles, or that's actually what we call a block sphere. So if I have a memory here of 2 qubits, okay, I can represent 4 different states. However, if I'm every one of them is pointing upwards, that is a 0, 0, okay, because this is a 0 vector. That's 100%. That will give you, if you run the equation, it will give you 100% 0, 0 state. If one is down, that becomes 0, 1. Another is down, that's 1, 0, just like your binary combination. And it could be both down. But we don't stop there. You can actually represent 2 states at the same time. What if I want to have the superposition of the first qubit? What if this turns to the right direction and the other one stays down or up? So you can have this. You have a superposition. You can represent 2 values at the same time. What if I want to perform an operation only with these 2 configurations? You can actually do that. Or you can do these combinations. You can actually do that as well, right? So that's amazing. So if I can do 2 at the same time, I can do 4 at the same time as well. So I'm there. This is the natural parallelism that for all of these states, you can actually perform computation already with just 2 qubits. You can have more if you want. Okay. So that's quantum memory. Sometimes we call that quantum RAM, quantum random access memory. So if for those who are a bit curious, there is no quantum ROM. Okay, not yet. Another concept is entanglement. Okay, so entanglement is another Ricci phenomena in quantum physics. So imagine 2 qubits. They met at one time, or physicists try to meet them at one time, and they perform an operation or form a procedure. So after that, they try to split those qubits or those electrons or quantum objects away. One probably is in US and the other one in the Philippines. So what happens is that if the operation is done in the US or either way, there is a direct correlation of what happened to the other. So if the other one suddenly spins upward and there is a correlation to the other, it will spin downward. And automatically that happens, and there's no wire in between. It's just quantum physics in between. So there's a lot of applications in that case. Actually, this is already done in China. So they have 1 qubit stationed on the Earth, and the other qubit was stationed, well, they sent it away on a satellite. They prepared it on a satellite. And what happens is that they try to perform an operation, the one qubit done on Earth. And they notice that the one in the satellite is also reacting. And there's no anything in between. There's no anchor to that. There's no Wi-Fi that's automating that. It's just pure quantum physics. And this already has been done in China. Right. So that's amazing. That's entanglement. There's a lot of there's a lot of benefits to do this. You can do this for computing. That means you can also perform parallel computing with more qubits in this case. Okay. Not even that means there is no, there's non-locality. It's not just beside each other. You can do perform parallel computation in a widespread of or a wider scope. Okay. Another application is in quantum communication. That means you can communicate with people with even less wires in between, okay, with higher efficiency. Okay. But then again, it's not faster than speed of light. There's nothing faster than speed of light. Okay, cool. I'm not going to go deep into this. Is a correlation always positive or negative? Is it perfect correlation? That depends on the quality of the entanglement. There is a quantum. We need to measure that as well. The fidelity, also the coherence of the entanglement. So it may not be in perfect correlation always. Okay, but there would be. It depends if positive or negative. It depends on how you prepared the qubit at that sense. Okay, there are preparations in that case, there are operations we apply beforehand, and that would dictate rather if it's going to be a positive or a negative correlation. So in that case, if we have information, we can also do operations, right? And we can do that by applying what we call gates or what we call linear operators in linear algebra. So what happens? How can you actually manipulate a vector to move up and down, left and right, rotate it 360? For those who've studied linear algebra before, that's what we call linear transformation. You apply a matrix onto a vector so that you can move it around. So what is the comparison or the similarity between this Boolean NOT gate and this quantum NOT gate, this X gate? So it actually flips values. But in classical, we only flip the values because it's 0 and 1. 1 becomes 0, 0 becomes 1. But what if you have a vector? That means you're flipping the whole direction, right? So how do we do that? So if I have this, the one goes up, another one goes down. So if those states, okay, if we represent the states again as get 0 and get 1, we have these. So our task is to find this M that flips 0 to 1 or flips 1 to 0, something like this. So what are the values A, B, C, D? Now you can use any mathematical tool that you want or mathematical technique, and I'll show you some answers here. So say, for example, if we have this operation right here, we have A, B, C, D, this M matrix here multiplied to some input vector, and there is an output vector, which is 1, 0 and 0, 1 respectively. So we can just use some analysis here. I'm not going to use any fancy math, just eyeball the values of the x's here. So this means the characteristics that's shown here for the first vector, or rather the first element, we see that it was switched below. So we're just trying to encode that into the second, okay, the second bit or second element of the vector. So that is the placement here. That means the value is now placed to the second one here. And the characteristic of this one, the second element of the first vector, becomes the first element of that of the output vector. So that means the placement or the one-hot encoding is 1. So that means M, this M right here, or this matrix applied to this vector, becomes this output vector. And M now is 0, 1, 1, 0. And that is equivalent to what we call the X gate or the quantum NOT gate. Okay. So it flips values. So it's not just limited to up and down. It could also be in any type of vector. And there's a lot of these. Okay. There's a lot of these switches and gates. You can actually play around with this later on. I think we're going to have rather an activity on this in the next few weeks, is how do you apply these, what we call gates, these operations onto quantum vectors, okay, or quantum bits, so that will have changing values. You can actually do this in mathematics as well. You can simulate this at your own pace, though. Yeah, cool. So if we have gates, for those who've been studying some logic circuits, that means if we have a certain Boolean gate, we can make a Boolean circuit. That's also the same with quantum. So if you have a quantum gate, you can create a quantum circuit. So in this case, this is an XOR gate. Okay, that's decomposed into the basic gates. You can make your own XOR gate. However, you can also do this in quantum, and this is the equivalent to that. And let's try to prove what happens. This is actually what they call a C0 gate, and these are other gates right here. So I would love to demo this, but I think this will be discussed in depth in the quantum gates in the next few weeks. So I hope you can enjoy that. So the idea here is that, okay, just already a spoiler for you. This gate right here, this XOR gate, the truth table to this is the same as the truth table of this one in terms of output. Okay. So these are other gates. We have the identity gate or poly I. We have poly X or the NOT gate. We have poly Y, poly Z, the Hadamard gate or the gate that induces superposition. And there is a Toffoli gate or a C0 gate, or sometimes you call it your XOR. Okay. So another concept here is that we need to have invertible computing. So whatever operation that you do to an input, if it's applied again, it should return to its original state. Okay. Say, for example, if we go back here, if we apply the X gate again or twice, this should actually revert back to the identity gate. So any of these, you can actually try it if you want. If you try to apply your Y gate twice, that's actually doing a matrix multiplication to itself. It will collapse to, or rather, it will revert to an identity matrix. So you can try. That's something that is observed as an operation in quantum. Okay, even the C0 gate. Okay, so you can try that in your own. You can challenge me that this would not become, this will not become I, but I assure you it will become I. So that is the concept of invertibility. So in a summary, so your quantum information is shown as such. Your classical bits can be either or, 0 or 1. Memory is 1:1. Your operation can be done by gates and Boolean gates and Boolean circuits, or logic gates and logic circuits. Quantum, on the other hand, can represent information as qubits. The memory is represented as QRAM, where it has 2 raised to n, 2 raised to n capacity, where n is the number of qubits. And operations could be done using quantum gates. There is another part here I did not discuss, is what we call the Hamiltonian. So the Hamiltonian is the configuration of all of these qubits going up and down, so on and so forth. These are actually the initial configurations for optimization problems that we can actually input to a quantum computer, and the quantum computer would solve it for us, just letting water flow. So I'd like to show an analogy to this. So imagine computing as driving vehicles, and what's the purpose? Is transporting people to one place to another. So the very basic one that we could have is a car. Okay, or it could be a motorbike if you want. So if you have a car, you can transport, let's say, 4 people at the same time, right? So that's the basic computing. Going back and forth for 1 hour, you can go back and forth and deliver some goods and stuff. But that's the basic thing. If you want it to become faster, you become a speed car, a race car that is increasing the clock rate, right? A PC or a CPU that has a higher clock rate rather than the regular one. So that's improving the performance of a CPU. Okay. What if you want to transport more people at the same time, at the same rate? You can actually use a bus. Now, buses, okay, could be an analog or the analogy to a GPU, because you can process more information or transport more transport or process more information at the same time. If you want to make it faster, just like the other GPUs of NVIDIA, you can use somehow like a train. So you're transporting more people at the same time and transporting faster at the same time, or rather at a higher speed. Okay. But note that these are all in land. They are best in land operations, right? But what if you're traversing through air or water? Can you use a car? Probably yes, if it's amphibious. Can you use a train? It depends if you have a tunnel underwater, or you have a very long bridge connecting to that. But that's the same thing as quantum computing. For the tasks that are very hard to do for regular vehicles or regular computing, it could be done easily or done specifically for that. For example, a helicopter. A helicopter could traverse you to one place to another in more efficiency, especially for long distances or unequal terrain. However, would you ride the helicopter every day to school or every day to work? Unless you're very rich, then that's fine, or your school has a helipad. But if it's not, but it doesn't, then that's going to be impractical, right? The same thing with quantum computing. It's not for everything that you're going to use a quantum computer or you drive a helicopter every day. Same thing with a submarine, or same thing with a cruise ship or a boat. Okay, probably you can boat if you want to boat, for example, Makati to Manila through the Pasig River. That's good. That's good for you if you want to do that. Also at your own risk, but that's possible. Okay, it may be efficient in some ways, maybe inefficient in some other ways. But that's the point. Okay, it's not always the best solution for everything. There is a case-to-case basis on where you can use this. Now, it's not an XOR problem that you only get to choose one. You can actually choose many. For example, right now, you're in your regular laptops, most of you would have CPUs and GPUs already at the same time, or especially for those who are doing gaming, right? That's the future that we're trying to see here, that there is a harmony wherein we can embed the QPUs together with the package, okay? So for example, a high performance computer having CPUs, GPUs, and quantum processing units at the same package. That is a hypercomputer, not a supercomputer anymore. So that's amazing, right? So that's the future that we're seeing. Though you can run everything on a quantum computer, but it's not practical. Just like running a helicopter every day. So it's not practical, but it could do the job done. But if you can have a better mix of these, optimize them, and distribute the complexities to each one, it would actually be better. Okay, cool. So how about quantum in the Philippines? Are we ready already? Are you ready for that? That's why we're doing this. We are doing this whole lecture series so you can be ready. But anyway, yes, we are pushing this. So quantum computing is just one part of the whole scene. There's actually another piece of this. It's called quantum technology. And quantum technology is a bigger field. And quantum information science is what I'm focusing here right now in this talk, or QIS. So quantum information science has multiple facets. It could be quantum hardware, quantum software, quantum computing, and quantum communications or quantum networks. Okay, so in quantum hardware, these are what we pertain to hardware devices, quantum sensing devices, quantum sensors such as X-rays. Those actually exist already, and quantum computer systems, quantum hardware, quantum calculators. Those exist. Okay, there's also quantum communication devices like quantum repeaters. There's also quantum network devices, other quantum network devices like a quantum teleportation device, something like that. And yes, you heard it right. There is a quantum teleportation device. There's also in the realm of quantum communication that's both in the on the hardware side, communication side, and also the protection side or encryption. That's where we have quantum cryptography. Okay. In quantum computing, we do have a lot. There's applied quantum software, there's quantum algorithms, there's quantum optimization, quantum AI. And that's actually what we're going to focus later on in this lecture series. How do we build quantum NLP? It's now in the realm of quantum computing, especially in QML or QAI. So in quantum hardware, we talked about this a bit earlier. So we have all of these different types of technologies, and you can actually look more into them. So we don't have a stand again. We don't have a stand. In quantum sensing, this is already one of the more mature aspects of quantum technology. Is that we have, for example, this is a device from a Singaporean startup and they're trying to find oil reserves using a quantum sensor, so that you don't have to do any type of drilling to find out where is the oil reserve. So even if it's going to be underwater. So in this case, it's actually non-invasive, and that's actually good for environmental purposes, and that also increases the efficiency of operations to gather resources. Quantum communication, quantum internet is our thing, so that we already have some standards in Korea in quantum network systems. I think the US as well is starting up its quantum network standards, as well as Germany. So quantum network is a combination of all of the quantum protocols and quantum communication devices out there that performs networking. There's also another type of network device called the quantum teleportation device. A quantum teleportation device transports or teleports information. Okay, let me just give more context about that. So when we try to teleport a bit, we're not, we're not teleporting just like Star Trek or what, or beaming up things. A quantum teleportation device, you prepare qubits, okay? And those qubits would have information inscribed to them, right? And at one end, a transmitter unit will destroy the information at one end, and that same information will be transmitted to a receiver unit, and that receiver unit will have that same value. So it's just like transporting information. However, the quantum channel right here, that is not mainly interceptable. Okay, so that means information is destroyed, so nothing can be retrieved in between, and that will just suddenly appear in some places. For example, you are in Mindanao, and suddenly you teleport your quantum bit to Visayas. That's actually possible if there is an existing quantum teleportation device. Okay. There's also the concept of quantum optimization under software. I would be excited to talk about this, but I think this is for a different webinar. So a quantum optimization aspect is in the applied sense. So this is for operations research for those who know about that, or optimization theory. So we apply all of the quantum equations here, or rather the classical equations, any mathematical equations that you have for optimization, we convert them into what we call quadratic unconstrained binary optimization, or QUBO, and then we transform them to Ising Hamiltonians. And Ising Hamiltonians are energy configurations, or what we call the initial states of all of the qubits. And that's something that we're going to run on a quantum computer, and the quantum computer will solve that for you. Of course, there is quantum machine learning. That's something that we are interested here in this talk, okay, or in this whole lecture series, that you can apply quantum machine learning or rather quantum computing in machine learning. You can apply machine learning for quantum computing, or you can do quantum computing inside machine learning. So there's a lot of flavors to that, and there's a lot of combinations. And I'm going to discuss this more on the next few slides. I do have specific slides for quantum neural networks. So there is a full quantum effort worldwide, and the Philippines is not lagging in terms of potential support. So that is here. We have a good amount of 860 million, quote unquote, 860 million in budget for the Philippines, and that we have already have good efforts in the sides of, especially the side of the government, and also in non-government organizations, and also some academia. Okay, so we're looking into that big push of a quantum effort. And we do have that, especially in the Philippines. We do have a quantum technology roadmap. And this is something that we're guided to do, especially, and we're not lagging in terms of capability building, especially with you guys here. You are helping the Philippines out in building a quantum ecosystem, a ready quantum ecosystem. So I did mention that you're trying to prepare all of these qubits, but do we expect to have them perfectly right now? No, they're not perfect. This is the concept of decoherence, or the coherence of information. So I mentioned earlier that when you prepare a qubit, in one case, is you put them into a near 0 Kelvin state. So what happens if it goes beyond 3 Kelvin or 5 millikelvin? The information could be lost. Okay, that's easy to be gone. It's gone, different value. So that's a bit crucial when we operate with qubits. So your computation would also be wrong, okay? Or the information is lost, especially if you have a lot of qubits, right? And that happens in entanglement. So if the entanglement was cut off, or rather it degrades over time, then the operation also degrades over time, right? So that's a big question mark, and that's a big challenge. And that's why we call it right now, we call it the noisy intermediate scale quantum era. Okay. So in this case, we are preparing ourselves for a fully tolerant quantum computer, so that when we have that idealized quantum computer, the algorithms that we're preparing would be already sufficient for that someday. But right now, we're trying to find ways to mitigate noise. Okay, it's both in hardware, software, and also other simulation things. So in hardware, you use error corrections or error correction hardware. In software, we try to do dynamic computing there. does that mean that electrons used for qubits are always manipulated near their ground state? Yes, they are. They are. So that is the main idea. Because if they're not near their ground state, there is still noise, and that vibrations would change the states of the qubits, and that will give you different values. Okay. So that's hard to maintain, especially those who know with physics, right? To maintaining it near ground state requires a lot of effort, and we're physicists around the world are doing their best to make this fault tolerant. And we're actually almost okay. We're progressing slowly but steadily to a fault tolerant QC. Now the question is, if it's buggy right now, why should we actually still use it? Right? We're taught in those in CS in IT that never to use an unstable package, never to use an unstable version. Right? That's a common practice. But we need to change this mindset in terms of this emerging tech. Okay. All right. Let's go back. Let's have a bit of a history here. So, AI history. Okay. If you're not familiar with the history of AI, let me tell you a story of how things began. It's like sounding like How I Met Your Mother. But anyway, the history of AI. Okay, it's not just way back in the 2000s. It goes beyond that. In 1940s. Remember Alan Turing, if you watched the Imitation Game. So that's the first very big practical use of artificial intelligence. Okay. And people love the idea. They love the potential of teachable machines. Okay. And that brings a lot of breakthroughs in the whole computing sense. Okay? And that's great. And people started researching a lot of things, and until they stopped. They stopped because the hardware could not keep up with the algorithms that they're thinking of, the theory. So people thought that this is a big no-no. They're not going to progress. We don't have hardware. Why should we actually start? Why should actually do this when there's no even no platform to do this? There's no way we can do that, right? So, however, yeah, that actually gave us the first AI winter. People stopped researching using AI until 1980s. In 1980s, we now have commercially available CPUs that could perform better processing, and people start researching again. That's great, and then they stopped. Okay, because we don't have enough computational powers again. Until we got in the years to come, is people started to believe in AI that there would be hardware that could be suitable for this. Until 2012, where in AlexNet, George Hinton's student, suddenly tried to use GPUs or determine the proper use of GPUs for training deep learning models. And then we got the boom in artificial intelligence again, since we have the right hardware, GPUs. So we had two AI winters that stopped the progress of artificial intelligence. But what if people didn't stop doing that? What if they had the way to work with artificial intelligence without, without having the expectation, or rather, they had the expectation of the hardware already in mind, and they have ways trying to simulate artificial intelligence? I think people would not stop researching, and we could have better artificial intelligence today, even better than what we have right now. If you think what we have right now is great, if we did research more back then, we could have this actually 10 years before, right? And that's amazing. And whatever we're going to have right now is already more amazing, right? So the same thing with quantum computing as an emerging tech. Here, the difference is we have the theory backing up the idealized quantum computer that it could work, right? And we do have ways that we could try quantum algorithms efficiently, just like what we have it as an ideal state, since we have the proper electrical components. We have CPUs and GPUs to simulate those. And that should not hinder us, since we now have the resources to do research on quantum computing. We're actually trying them out already of quantum computing, so that you can apply it to a real quantum computer in the next few years. And we're preparing all of the software. We're just going to plug and play that once we have the quantum computer. And there's a lot of migration software already that tries to help you code in quantum without a quantum computer. But once it's ready, you can transfer your code into the real quantum computer, or even test it out with the existing quantum computers. Okay, so now is a great time. Imagine you have early access to a very cool technology. It's like having AI before it was cool. You're a hipster. That's great. So we're at the stage we're like the EDVAC and ENIAC of computing way back in the 1970s. Okay. And that's, imagine that as being cool. You're the pioneers. Your batch are the pioneering people that are gonna try quantum computing even before there was a real fault tolerant quantum computer in the Philippines and the whole world. And that's already a good start for everyone right here. So yeah, I think we have a lot of potential here, and we have a lot of tools so that you can be prepared as well. Okay. So let's do some applied quantum computing. Okay. How can we actually use this in real life right now, not wait for the next 5 years? So in the life sciences, quantum computers, quantum annealers are good at optimization. So RNA folding, drug design, all of those are actually convertible into optimization problems that could be done on a quantum computer. And we already have papers on this. So we have also this for protein folding. This is already existing, and our papers out there that already shown a significant advantage. The earliest applications of quantum computing was actually in finance. So in for example, portfolio optimization and also stochastic processes. We also have quantum finance for that. Okay, optimization and so far, so on and so forth, and also credit risk analysis. We already have again a lot of papers on this. Of computer science and security, we have quantum key distribution and post-quantum cryptography. It's not here. Um, but these are ways in how to perform network security using quantum algorithms and even post-quantum algorithms. There's also pattern recognition. You can use quantum neural networks or use quantum neural networks to improve artificial intelligence. So we do have what we call hybrid quantum neural networks, something that is a platform, or rather an algorithm design, and how you could run a quantum computer inside, or a quantum computing algorithm inside a neural network, let's say a convolutional neural network, a artificial neural network, an LSTM, RNN transformer, and so on and so forth. You can hybridize that by improving even one part of it as a classical, or rather a quantum neural network. Okay. This takes advantage of both quantum computers and GPUs and CPUs at the same time. So this like a proof of concept of how we envision the assemble the assemble of all of those processing units someday. And mind you, there are improvements already. I have recent researches that improves forecasting, okay, and classification problems, but not all of them, using hybrid quantum neural networks. If those are electrical engineering, if anyone here is also in EE, I'm in EE. So my PhD now is already in EE. So we apply this in, for example, microgrids, renewable energy planning, assessment of power systems, reliability analyses. We can also apply them there. There's a lot of applications in the electrical engineering space. In industrial engineering, we have the traveling salesman problem for supply chain management, distribution networks. We have bin packing problems for cargoes. These optimization problems can be done in classical, but have significant speed advantage when you do it in quantum. Okay. In communication, I did just discuss before, we have quantum networks, or the quantum internet. And we also have optimization problems such as cell tower placement. That's more on the operation side. And we do have a lot of resources already for quantum in communication. So if for those who are in the communication field right there, please feel free to check these out. Now, how do you get started? So you get started with this lecture series. Okay, that's the best thing. But in the terms of tools, something that you're going to encounter later on, IBM is right now is the leader in the superconducting qubit quantum computers. So they have a platform for this. You can actually use IBM quantum simulators and Qiskit. I think that's something that's going to be taught in the next few weeks. And how do you program a quantum computer? So imagine you remember these symbols right here are the gates. These are the operations. Now you can create your own quantum circuit, and this could, create your own circuit. And this is actually the example of Grover's algorithm in quantum circuit form. And there is the corresponding code here. This is QASM. This is the quantum assembly language. That's the equivalent to this symbol right here. Cool, right? We also have this quantum annealer. That's a D-Wave. So if you want to run optimization problems, you can also run this. I have used D-Wave before for several researches, specifically for optimization. And there are other available platforms such as QEra, Continuum, Rigetti, Microsoft, Intel, and Fujitsu are already making their own quantum computers as well. So yeah, cool, right? So question is, I don't have a quantum computer. How can I even do this? Right? So how can I have the advantage of quantum computing or even try having good quantum algorithms if I have a CPU? Okay. And that's cool. Actually, Qiskit would be could run a quantum simulation in there. That's actually good. However, you can actually make it better, especially if you have a gaming computer. Okay. So there is what we call NVIDIA CUDA Quantum, or rather NVIDIA Quantum, QQuantum. NVIDIA QQuantum, if you guys are doing artificial intelligence, have you heard of CUDA before and CUDNN? It's a similar thing. Instead of accelerating your hardware for AI, this is accelerating your hardware for quantum computing. That means you can run quantum algorithms efficiently with a GPU. That means you have a better way in simulating your algorithms faster than compared to your CPUs. Okay. So you can actually use this. You can install QQuantum, and that could help your computers improve it. Although a caveat here is that you need to use Linux. Okay, QQuantum is not available on Windows. Okay? So if you ask me why, it's because probably the developers are still working on it, especially for Linux systems. But there is another way. Although still in Linux. You can use NVIDIA CUDA Quantum. There is a cloud option to this. Actually, you can use NVIDIA CUDA Quantum on Google Colab if you're familiar with that. That means you can run all of your simulations and configure your hardware, NVIDIA hardware, to run a hybrid quantum algorithms, okay, that can run both on a quantum processing unit and a GPU at the same time. Although accessing to a QPU would require you to have subscription, so that's another issue. But in this case, you can even fully run this on a GPU. So that's it for everything so far. If you have any questions, I'd love to connect with you, especially if you need some help on ideating on a research, pushing for a research, or you want to know more about the other slides that I did not really add discussed in depth. Okay, so especially with the physics side, the quantum AI side, those are other parts that we discuss in a separate webinar. So if I love to connect with you, or you can reach me out through the organizers, Jabez as well, especially our director for our activities and community development. So yeah, thank you. If you have any questions, I'd love to answer them. Thank you.
So again, thank you, Sir Dylan, for the intro to quantum computing. So, okay, let me share my screen. Okay, so before we continue with the lecture series, so first let's have a 5-minute break. So yeah, let's have some water break muna, and then let's recharge for the next session. Yeah, okay, now so resuming our session. Okay. So first, may I call on Sir Elmer Paramo, the project lead of Itanong Project, and senior science research specialist at TOST ASTI for a special message. Hello po, sir.
Thank you, John. Yeah. Good afternoon, everyone. Thank you for tuning in dito sa ating lecture series, no? QNLP lecture series. Maupay nga kulop haiyo nga tanan. Okay. So meron akong coach dito. I ask him how do you say how do you say good afternoon sa mga kaibigan natin dyan sa Tacloban. And it's really our honor, no? The whole days quantum natural language processing. It's really a pleasure to welcome all of you. I see here, no, I'm really excited to see more than 250 participants tuned in, and I do apologize for tuning in late because I just finished a class. I'm also teaching kasi in one of the universities here in Manila. I'm Elmer Peramo of the Advanced Science and Technology Institute. I'm the project leader of the Itanong. Yung Itanong, uh, it's a AI project, no, more on large language models to interface a natural language relational database management systems, no, so that you can use natural language to interface with those databases. So that's the idea. It's kind of like I would say, no, roughly a Filipino version of ChatGPT. Anyway, sige. This event is proudly sponsored yun nga by DOST ASTI's Itanong team, and then One Quantum Philippines, which is I'm also a part of. And we are really grateful, no, to our host and partner and sponsor from UP Tacloban. I'd like to thank Doctors Yuxiong and Arinto for this partnership, and also with DICT Region 8 and also UP Interactive Society and Dev 8 for making this gathering possible. So ayun, excited na ako sa mga susunod pang mga oras, and also for the next series. By the way, ako yung magiging ninyo pala, teacher ninyo, or for next week. So I hope you look forward to that po. And ayun, basically I just would like to welcome you po dito sa na to, and let's dive into the latest scientific breakthroughs, no, in mga emerging technologies like quantum computing, natural language processing, and very relevant po ito, no. And I hope, no, na marami tayong matutunan at ma-share din natin itong ating magamit itong mga matututunan natin dito sa lecture series nito. Yun lang po, maraming salamat po, and welcome po sa sa Quantum QNLP Itanong and One Quantum Philippines with UP Tacloban lecture series. Sige po, thank you po again. Back to you, Jan.
Okay, thank you, Sir Elmer, for the special message. Okay, now, so moving forward to the lecture series. So let me introduce the next lecturer. So he is the Skill Building Programs Manager at Kada Career, Strategy and Partnerships Team Lead at Quantum Education Fellowship, QCSP, and then the Director of Operations at QCSP. Okay. Hello, Jabez.
Hello. Yeah. Wait, let me just share my screen. All right. Wait, let me share screen. Bagal na po ang aking laptop. So, yeah, this yeah. Welcome everyone. Hello, hello. Welcome to our QNLP lecture series. Ayan. Before we begin, yung part ko at least, let's answer some Q&A. May apat dito. Ayan, so first, does an NPU will help the quantum computing? So, as Sir Dylan said, na maraming ways on how we can mix and match, ayan, yung ating mga processing units, no? Pwedeng CPUs, GPUs, yan yung default ngayon, and then you add the NPUs and then the QPUs. We can definitely use AI to improve quantum research, like improve natin ang paggawa ng quantum technologies using AI. At the same time, pwede siyang baligtad naman. We can use quantum to improve AI workloads. And then pwedeng both, like one workload to using both NPUs or GPUs and QPUs as well. Yun yung tinatawag na hybrid quantum computing or hybrid neural networks rather. So, and then another question, can we rely on the cloud for quantum computing instead of a local GPU? Yes. Ayan, so personally ako rin, I don't have an RTX 2080 or higher na GPU, hanggang ano lang po ako, hanggang Radeon graphics lang. So yeah, we can definitely use cloud-based services. So pwede yon kung simulator, as Sir Dylan said, pwedeng manghiram ka ng instances sa cloud and then do your simulation there. Sa DOST, meron din silang simulator. I'm not sure kung pwede na tayo maka-access yung public, pero they're building a quantum simulator. Meron ng a lab doon. So yeah, if itong lab na to, itong logo na ito, itong kulay orange, no, that's our Quantum Innovation Laboratory. No, and yung flagship project ng DOST ngayon is the Quantum Circuit Simulator project or QCS project. You can search them up. So, nasa Facebook sila and others. No, so that's for simulation. And then of course, naka-expose na. Mayroong mga APIs na naka-expose or parang their services for real quantum hardware naman. So later, I'll show you yung iba-ibang mga hardware as well. I guess that's it for that question. And then another one, why are there variations of quantum computers being built? Is it because, is it based on the technique of inscribing information? Yes, based siya. Kasi when we say quantum, later I'll discuss more about this. No? Pero may iba-ibang ways, may iba-ibang systems, may iba-ibang quantum systems, and they all have the capability dun sa quantum phenomena like superposition, entanglement, tunneling, state collapse, and other phenomena. So we can use those for computation. Ang tanong is, ano ang the best at ano ang scalable? So yun yung race ngayon na kung sino ang mauna would probably earn lots of revenue. Ayan, kung sinong company ang ano yan. Next, yeah, ito naman more on logistics. Will we be able to receive the PPT file soon? We'll try to send it, pero definitely we'll send materials to you guys. Let's see if we can send the file, the PPT itself. Pero the recording will definitely send it to you as well. Ayan. I think ito mga questions. Sige, we can answer this as well. What are some practical applications of NISQ in fields like metrology or atmospheric data analysis? Are there any relationships that you may share? Ayan. Meteorologist. Personally, I haven't explored that yet. I think, yeah, maybe we can ask Sir Dylan. Yung explore ko pa lang sa QML is more on the healthcare side. So, andyan po ba si Sir Dylan? Hi, sir. Ay, na-disconnect. So, yeah, we'll get back to you on that. Ayan. And then, ayan, for the last question, Sir Bobby is already typing an answer. Ayan, oo. Sige, let's start. Let's start the session na. Yeah. Okay, so my portion would be qubit modalities or different ways to do quantum. Ayan, tamang-tama yung question kanina. And the quantum computing toolkit. Ayan, meron ring questions about how you can get started on this. So let's have an outline. So again, hardware approaches to quantum, or as we call modalities. Now, qubit modalities. So qubit is the quantum bit. Ayan. And we will discuss gate-based versus analog or other paradigms. The criteria to make a universal gate-based qubit. Ayan, may criteria. Yun yung dahilan. No? Itong mga ito, superconducting, trapped ions, kaya nilang masatisfy yung criteria. That's why we explore all this. Ang tingnan na lang natin kung ano ang pinaka-the best at kung ano ang pinaka-sustainable. And then, ito yung mga specific modalities. There are more than this, pero ito yung mga matunog lately. So, superconducting, trapped ions, photonics, or and then spin or quantum dots, and then neutral atoms. Later, I'll show you some examples of neutral atoms, since that's my favorite. Medyo biased ako. Pero yeah, that's my favorite right now. Comparison of qubit modalities, of course. And then we'll also dive into how we can start working with quantum and like the toolkit, no, parang the overview of how it works and the tech stack, no, ano bang, syempre, computer yan, hindi lang naman yung mismong QPU, maraming factors dyan, programming languages, simulators, and other frameworks. Ayan, so let's have a recap. We humans don't operate on the quantum scale, so we can use these special phenomenons on the quantum scale to solve the problems on the macro scale, yung scale natin, no? Hindi naman tayo pwede mag-occur on two different states, di ba? Like, we just exist, unlike the Schrodinger's cat, di ba? Yung ganun. Pero, we can definitely leverage the quantum scale to solve yung problems natin. So, this is basically like a general view on right now on how we use quantum computing. So, let's say we have a classical, as we call it, or a real-world problem, for example, logistics, no, or sa medicine, or kung ano man yung pinakita na applications kanina, we convert that. Now we have a quantum representation of that problem, no? And then we use quantum computers to solve that problem, no, in the quantum realm. And then kunin natin yung result, no? Ilalabas niya yung result, and hopefully we can use that result for real world impact, no? That's basically it. And yung classical problem, marami tayong problema sa ngayon, marami tayong pwedeng i-solve na problem, and using it, no, pwede rin, classical naman yun, magigets naman natin. Ang i-dive deep natin on this lecture series is how to represent the problems into quantum representations and different ways to solve them using different technologies as well. And just some expectation setting, katulad ng sinabi kanina ni Sir, quantum isn't advantageous on every computational work. For example, quantum computer can't host a website, or it shouldn't. Kasi nandiyan na yung mga computers natin and can send an SMS. But for those hard and specialized problems that are classically intractable, yan, quantum might have an edge or an advantage. Yun yung sinasabi natin, quantum advantage or minsan quantum supremacy even. Now again, classically intractable, yun yung mga problems na unreasonable. Hindi siya reasonable na gawin mo siya sa laptop mo or sa supercomputers, and it would take up centuries to solve, or it would need a lots of memory. So yung complexity niya. So we will have like a session about complexity and ng classical and quantum algorithms in the future. Ayan, so let's start with information. Ayan, so if we have a problem, ang gusto natin, makakuha tayo ng maraming information about yun. And then using that information, we try to solve it. So we can represent information multiple ways or in different ways. We have here analog signals na parang continuous, pwedeng 0.1 volts. By the way, I'm a student sa electronics engineering, so makakita kayo ng maraming mga analogy sa electronics now. Pero yeah, analog signal can be like 0.5 volts or in between. And then we have digital signals, which are ones and zeros, no, and mas abstract sila. And another way to visualize it, ito analog would be yung smooth na spectrum, and then digital would be like specific and then yeah, and you know this. And then at the same time, kung meron ganun sa classical information, there's something also similar on quantum information. Now we have analog and digital. So analog plays more on quantum dynamics, no? Pwedeng energy states, no? Energy states ng yung quantum system. And then pwede ring digital, no? Meron ka pa ring states, pero parang naka-define na. So again, dito, you have from 0 to 5 volts. There's infinite ways, there's infinite values doon. Pero sa digital, you just have 0 volts or 5 volts. Parang defined states sila. So this is something similar sa quantum, no? Analog energy levels, iba-iba. No? Pwedeng may topology ka, tapos mayroong mga atoms dyan, tapos kung paano sila nag-interact, that can be analog. No? Pero pwede ring digital. No? Parang yung sinabi ni Sir Dylan kanina, meron kang up state, meron kang down state, and then doon lang siya naglalaro. No? Pwedeng sa gitna, like 50-50, pero kapag at the end, i-measure mo na siya, magsasnap siya into one of those possibilities. So digital pa rin. No? So yeah, later I'll discuss more about dito, like how does it look like kapag actual representation na. Pero yeah, we talk about information, pero we also need to talk about na kailangan natin ng medium to realize that information. Ayan. So, yeah, for example, voice. That's a form of information, di ba? And ang medium niyan is yung pressure sa air, di ba? Ayan. So, we have compressions and rarefaction sa air. And yung air, siya yung magdadala ng energy, ng information, hanggang mapunta sa tenga nyo. In this case, dadaan mo na ng computer. Anyways, and then visually, sa light, optically rather, information, nakapatong or parang naka-carry siya ang information through EMF waves or electromagnetic waves. Ayan, we have here the electromagnetic spectrum, no? Ayan, gamma rays, X-rays, no? And of course, visible light. And then, sa mga communications engineer dyan, microwaves, ayan, yun yung physical medium. And then, eto, ayan, sa mga, hindi mga oldies, nabutan pa rin naman namin yung mga yan. Pero, mga discs, no? Optical discs, na parang may laser, tapos based dun sa grooves, no? Grooves or pagka, parang may scratch, kung paano naka-scratch yung disc mo, na dun naka-store yung information. Tapos iikot yan na mabilis, and then, syempre, yung ilaw, yung pag-bounce ng laser, parang mag-blink-blink siya, yun na yung information mo, di ba? And then, sa mga ano natin, sa mga SSDs or yung mga devices natin ngayon, no, they're stored electrically naman. Di ba? Sa mga, ayan, mga non-flash chips, mga memories natin. No, pwedeng magnetic, pwedeng is kapag hard drive, magnetic, no? Mayroon kang umiikot na magnetic disk. And then ito naman, mga solid-state devices, electrically controlled naman sila. So just like how we can realize information on a physical medium sa classical, we can also do that in quantum. So ano ba yung mga pwede nating paglagyan ng information? So it can be a quantum system na electrons, photons, atoms. Atoms would be neutral atoms. Ions would be positively or negatively charged atoms. And then pwede rin palang circuits. I think we can discuss about those later. Circuits and more. Marami pa. Sobrang dami. Every time, mayroong bagong ways na as long as masatisfy yung criteria. And then, kapag na-store na natin yung information on a system or on a physical system, we use that for computation. Now, wala namang sense kung i-store mo lang, wala ka nang gagawin, di ba? O, mas maganda if you can use that for computations. So, we have here, again, the criteria. We call it the DiVincenzo criteria. Actually, bago pa lang to, like, buhay pa si DiVincenzo. Ayan, narinig ko lang siya mag-talk like last year on a webinar. No? So really, talagang cutting edge talaga ang quantum ngayon. And yung mga late soon, no, yung mga algorithms na i-introduce namin in the future, most likely buhay pa yung mga nagsulat or nag-design ng mga algorithms na yun. So DiVincenzo, naglagay siya ng parang checklist on how you can construct a quantum computer. And first is a scalable physical system. Again, physical yan. Dapat meron akong physical system. And well-characterized qubits. Basically, a layman's term, well-characterized means, alam mo, para meron kang define na states. No? That's why more likely parang gate-based approach tayo. No? More defined. 0, 1. Yun lang. Diba? Kaysa dun sa infinite values, diba? Mas madali akong 0 or 1 na lang. So, that's one way to create a well-characterized qubits. And then another keyword here is scalable, di ba? Dapat pwede kang gumawa ng maraming qubits at the same time do it on cost-effective manner. Next is the ability to initialize the state of the qubits on simple fiducial states, or layman's term, you can put them reliably to a starting position. No? Like a starting position, pwedeng ground state, yun yung pinaka-baseline state mo. And then you can go from there. Like, let's say yung 0 mo, and then kapag nag-apply ka na ng operations, yun, dala mo siya sa 1, dala mo siya sa superposition and all. Pero before mo gawin lahat ng yun, dapat malagay mo muna siya sa isang starting position or fiducial state. And then, long relevant quantum coherence time. Coherence time meaning, yan, your quantum system can retain the quantum information. 'di ba? Dapat kaya niyang i-store for a certain period of time, no? Para makagawa ka ng computation. So wala namang sense siguro kung 1 millisecond or one instant lang yung quantum information tapos mawawala na, 'di ba? Sayang naman. So dapat mayroon kang period, no, na magsistay yung information doon, tapos gagawin mo lahat ng operations mo and then kunin mo na yung output bago masira or bago ma-decohere. Ayan, bago maalis yung coherence ng system mo. And then a universal set of quantum gates, no? Basically, you can do all the fundamental operations on your qubit. Yan. So kung gate-based yung gamit natin, na for example, sa mga nag-aaral ng ano dyan, ECE or Computer Engineering or CS, no? Sa mga logic gates, di ba, we have the universal gates na NAND gates or NOR gates, di ba? So as long as you have that gate, you can do every other gates na. Like, ibuo mo lang sila, you can do other gates na. So this is something similar sa quantum, no? Dapat yung qubits mo or yung modality or yung approach na pipiliin mo can have that universal set of gates. And lastly, you can measure, no, your qubit. You can reliably measure the value or state of your information sa dulo para para makuha mo ulit yung solution ng problem na sinosolve mo. So wala namang sense siguro kung mag-store ka ng information tapos mag-operation ka tapos masisira lang pala or nonsense lang yung mababasa mo sa dulo. So yeah, we have some questions here. Ayan, can we use quantum computing for genomics and or drug discovery? Yes. That's on the realm of quantum simulation and quantum chemistry. Ayan, so again, kapag mga covalent bonds, yung mga ganun, yung mga chemistry, yung mga bonds na ganyan on creating new materials, di ba? That's governed by quantum mechanics. So of course, if you can simulate your system in a quantum computer, that can definitely help on creating new drugs. Ayan, nag-send si Sir Dylan ng mga links. Ayan, hard photons. Ayan, lately, mamaya, ayan, we can do the next, merong time portion for photons. Ayan, so again, ito yung some of the ways that we can do quantum computing, or ito yung mga modalities that we can do. So first off, when we think of quantum, electrons agad, di ba? As an electronics engineering student, electrons talaga yung linalaro natin. Pero from contrast with what we do right now, no, kapag yung 1 natin is kapag may nag-flow na electrons, 0 kapag wala. In this case, yung information natin sa mismong electron. So, ilalagay natin yung information on the spin of the electron. So, if you remember from your chemistry classes noon, yung spin up, spin down, that's it. No, that's it. And yung if you remember yung mga quantum numbers, ayan, that's what we're talking about. So, what we do is, parang we get a silicon chip, no? I think that's one of the advantage nito is silicon chip yung gamit niya. So yung mga CMOS na gamit nating fabrication ngayon, we can parang adjust them and then adapt them to do this spin qubits or quantum dots as they say. Itatrap mo yung electron mo dito and then ito yung mga control surfaces mo. And then mag-fire ka ng microwaves or kung ano bang uri ng operations that you would do, usually RF signals yung gagamitin mo, to flip yung spin ng electrons. No? So talagang, isipin mo yung imagine, no? An atom, tapos meron siya umiikot na electron, or hindi naman umiikot, pero like, nasa orbital yung electron, and then papalitan mo yung property ng mismong electron. Diba? Imagine how sensitive your equipment should be, diba? So, ayan. Question, will those set of universal quantum gates also have logical equivalences similar to classical logic gates? Yes, there are logical equivalences. Katulad ng pinakita ni Sir Dylan kanina, yung chart na yun, that's it. Ginawa yung mga logic gates using quantum logic gates. Ayan. Anyways, ayun, some pros ng spin qubits, it leverages existing semiconductor technology. Ayan, for example, ito, Intel, di ba? Okay yung mga fabs nila. So meron na silang fabs, i-adjust na lang nila for spin qubits. And then strong gate fidelities and speeds. Gate fidelities means, paano ba explain? Kapag nag-apply ka ng gate or nag-apply ka ng operation, na maa-apply siya ng maayos. So for example, imagine natin yung block sphere or yung state natin. Kapag nag-apply ka ng laser or ng RF wave, no, dapat ma-flip siya ng maayos. Yun yung fidelity na pinag-usapan natin. And since we're working with electrons naman, mabilis naman yan. And then cons niyan is it requires cryogenics. So dapat talagang shielded yan. Kasi again, electrons yung pinag-usapan natin. Stray thermal noise lang or kung anumang noise, no, can destroy na yung ating quantum state. And then only if you entangle gates to date, ayan, and mabilis silang maalis sa pagka-superposition nila. And then of course, since nakatrap sila, no, tabi-tabi or pwede silang mag-interfere. Pwedeng yan, interference and crosstalk, di ba? And usually electrons mailap yung mga yan, di ba? That's the basis of conductors, di ba? Lipat-lipat yung mga yan. So, yeah, how can we trap those electrons on those? Ayan. Next, photons. Ayan, may question kanina, photons. We use photons since it's a quantum system, no? And we can store yung superposition. Pwede sa arrival time niya, pwede siya sa polarization, kung vertical or horizontal polarized siya, and iba pang mga properties ng photons, no? And ang convenience naman dito is pwede natin siya agad gamitin for quantum communication since nagta-travel na yung photons natin, no? So for example, this is how an actual circuit would look like, no? Yan. Tapos kapag nag-join sila, pwede kong ma-zoom to. Ay, hindi. Pero ito, kapag nag-join or nag-meet sila dito, pwedeng dun mag-entangle yung mga photons natin. Diba? So, ganun yung ginagawa sa photons. So, ang pros nito is extremely fast gate speeds and promising fidelities dahil nga we're operating at the speed of light and no cryogenics or vacuums required. So, cryogenics dun sa mismong fiber hindi kailangan. Yung vacuum hindi rin kasi nga sa fiber lang siya maglalaro or pwedeng waveguide. No? And overall, small footprint lang. And we can leverage existing CMOS fabs. So kung familiar kayo sa photonics, photonics ICs, no, we can leverage those as well. Ang cons naman dito is noise from photon loss. Kapag na-absorb yung photon, no, kapag tumama siya sa isang atom, na-absorb siya, wala na yung qubit mo, 'di ba? And again, each program requires its own chip, no, kasi this is fabricated. No, fabricated na yung algorithm mo or fabricated na yung use case mo. So, yeah, it's great for specific use cases. Pero if you want yung general talaga, no. And then, photons don't naturally interact. Hindi sila gaano nag-interact. So, that's a kind of a con. No? There are companies that are working on this. We have Quantum, Xanadu. Xanadu is on fire lately. Now, Quix Quantum or computing and a lot more. So, usually bandang Europe or US since malakas yung photonics industry nila doon. Next is atoms. Ayan. What if we use neutral atoms for quantum computing? Again, we use neutral atoms para hindi sila mag-interact like electrically or magnetically. Ang pag-interact nila, mag-interact sila pero mass controlled. No, instead na ions, which we will discuss later. Pero in this case, neutral atoms. For example, rubidium atoms or cesium atoms, pwede natin silang gamitin. So what we do is we trap them using light or lasers. Ayan, so parang meron kang tweezer, gamit mo light, tas tweezer. No, tapos hawakan niyo yung atoms, no? And hindi lang pwedeng isa, pwedeng marami. For example, here we have 16 atoms, parang meron kang matrix or array of atoms. And then pwede mo silang move around. No? Ito yung kagandahan sa neutral atoms. No? I-point mo lang yung laser, igalaw mo yung laser, parang ginagalaw mo na rin yung atom. And you can create different geometries no, that can represent different problems. So, for example, it can be yung dito sa likod, yung hexagonal arrangement. Ito, if you squint ng kaunti, ito yung map ng Earth, no? Yung land masses ng Earth. So, yeah, kung squint mo konti, ayan, di ba? So, you can represent like different kinds of problems using this dahil super flexible ng ganyan. So, ito, ang pros naman is long coherence times since neutral atoms sila. Uh, as hindi sila as parang affected by stray electrical, although of course affected pa rin naman. Atoms are perfect and consistent, very similar, no? One rubidium atom is almost or very similar to another rubidium atoms. Strong connectivity, and including more than 2 qubit gates, and external cryogenics is not required. So hindi mo kailangan i-cool ng sobra-sobra. Kasi yung pag-trap mo pa lang, ultra cold na yung ano mo doon. No? Kasi 'di ba kapag temperature, it's just you can look at it as kinetic energy, 'di ba? So kung tinrap mo yung atom such that hindi na siya makagalaw, you basically cooled it to that point, 'di ba? So no need na. And then cons nito, it requires ultra high vacuums. So kung meron kang vacuum tas may rubidium atoms ka sa loob, hindi pwedeng may ibang lumilipad lang na atoms diyan. So baka ayos, perfect nga yung mga rubidium atoms, matamaan naman siya ng ibang atoms. So hindi rin pwede. And also laser scaling challenging. Dapat super accurate ng mga lasers na ginagamit mo. Very very specific frequency ng laser, no, very very straight yung mga lasers mo. Hindi pwedeng magkaroon ng turbulence on your laser. No, at the same time, that makontrol mo sila ultra high precision, no. Imagine ang dami mong kaya nga ito ang complicated ng setup. Ayan, so maraming mga optical ano diyan. And then yeah, some of the companies working on this called Quanta, Atom Computing, Pascal, and QEra. Mainit-init rin to lately. Na marami silang mga release Harvard-based yan. And then trapped ions, positively or negatively charged particles. We use them. I-trap mo sila using electrical fields and magnetic fields, of course. And then, pwedeng sa oscillation nila, kung paano sila nag-move together, you can encode information na doon. Ganun sila mag-interact with each other. So, ang pros nito is, yan, high gate fidelities and long coherence time. Extreme cryogenics, hindi gaanong kailangan kasi naka-trap naman sila na maayos. And then, ions are perfect and consistent just like atoms, no? Kasi buong atom na yung you're working on like a large, fairly larger atom, imbes na electron, diba? So, mas manageable. Ang cons nito is slower, mas mabagal yung operations natin. So kahit na matagal siya maghawak ng information, matagal rin yung operations, no? Matagal mo, for example, no, matagal mo nga siyang mas konti yung gates na pwede mong i-apply dahil mabagal. No? Lasers are hard to align and scale, and you still use lasers for this, hindi lang magnetic and electrical fields. Ultra high vacuums required just like neutral atoms. And ion charges may restrict scalability. Ayan, again, although we can leverage yung attraction sa ions, no? At the same time, it's kind of like, it also like, they would interact through and through kahit na ion natin. Diba? So it's a matter of balancing and leveraging those kinds of properties. So ito mga mainit-init rin itong mga companies na to, IonQ and Continue, one of the biggest quantum companies lately. Ang laki ng investment dyan sa Continuum lately. AQT, ito Turkey-based naman ito, Universal Quantum and Oxford Photonics from, of course, Oxford. Ionics pala, sorry. And then circuits, ang dami, no? Ang dami talagang ways kasi nga nasa-satisfy nila yung criteria, yung DiVincenzo criteria that we did, we shown kanina, nasa-satisfy ng mga ito. So it's a matter of ano ang the best for specific solutions. So it can be one, katulad ng transistors sa electronics, or it can be multiple, pero specific use cases. So let's see in the future. Superconducting qubits, this one still uses yung mga fabs na ginagamit natin ngayon, CMOS fabs. Pero we use superconducting material. So pwedeng aluminum or other compounds. And then we basically create like an LC circuit or parang an oscillating circuit. No? So this one is a electronics version. We have here a capacitor and then we have an inductor here. And then very similar, pero imbes na inductor, we change it with a Josephson junction. Ayan, it's made with a superconducting material. So again, it's an oscillating circuit. So kung paano siya mag-oscillate, no, sa mga states niya, dun tayo naglalaro. Dun natin in-encode yung information. For example, if it's oscillating at this energy level, no, yun yung sabihin natin ground zero or state zero. And then, kapag tinaasan natin ng energy, it oscillates on this energy level, that would be state 1. And then, yan, parang nag-jump ka on those states. Again, hindi po pwedeng nasa gitna, no? Hindi pwedeng nasa gitna yung state mo. It should be 1 or 0 or a combination of those, like superposition. So this, medyo blur, sorry. Pero this one, I think is from IBM. Ayan, and yeah, I won't discuss that anymore. Pros nito is high gate speeds and fidelities dahil now we're working with circuits and presently available silicon processes. And yeah, standard lithographic process. And yeah, ito dahil nauna ito, yan, maraming mga companies talagang nagpo-push for superconducting qubits, such as IBM Quantum, Google is doing superconducting, Rigetti, or Oxford Quantum Circuits, IQM. Ayan. And ang cons naman nito, again, superconducting needs cryogenic cooling. And dapat talaga super low para makuha yung superconducting capability. So, need nating makuha itong TC or critical temperature natin para mag-superconduct na siya. So, that's in the range of 10 millikelvin, 10 to 20 millikelvin. So that's colder than space. So I think that's the coldest area in the world ever. So ayan. Yeah, just a simple parang compilation or comparison of this. So we have superconducting qubits. Ito, as we can see, parang ayan, mabilis ang gate speed nila, mabilis silang mag-interact, no? Ayan, pero sa performance, mid lang sila. And yeah, sa gate fidelity. Ayan. And then silicon quantum dots, ayan, pahabol sila, no? Ito yung mga spin qubits, no? Humahabol sila sa superconducting. And then neutral atoms, no? Medyo mabagal yung gate speeds nila. Ito, nandito sila banda. And medyo mababa yung gate fidelities, no? Pero there's a lot of improvements done already. I think this one is 2020 pa ata. Ayan, marami ng bagong research dyan. We have here trapped ions. Ayan, best performance based on this survey. Pero yeah, nasa mabagal din sila. And then we have here NV centers or nitrogen vacancy centers. So instead na atoms, yung holes. No, yung vacancy, yun yung pinaglaruan natin. So pwede yan like diamond vacancy centers or other colored vacancies. And then yeah, iba-iba pa, mayroong mga dope nuclear, nuclear magnetic resonance, yung mga ganun, marami pa silicon MOS dots. Ayan, may magkakaiba lang sa silicon quantum dots. Ayan, ayun, basically key takeaway dito is there's a lots of possible na mga potential na mga technologies. Hopefully we can we can do research dito in the Philippines in the future sa ganito. Right now, makigamit po muna tayo ng makigamit muna tayo ng computer. Pero yeah, nakita natin iba-iba yung pros nila. Meron na tayong mga presently available processes like yung mga silicon-based na at the same time meron ding mga hindi kailangan ng cryogenics like neutral atoms and photonics. And then meron rin naman na ginagamit lahat like trap ion. So it's a matter of kung ano ang the best and kung ano ang scalable and reasonable gawin. Now, wala pa tayong quantum computer dito sa Philippines. What can we do? Ayan, so we can access computers outside. Ayan, yeah. So this is the quantum stack. Ayan. So kung mga developers po kayo, you're familiar with stacks, tech stacks, or kung computer engineers na meron ring classical computer stack. So we have here applications, yan, development management, workflow management. So ito po yung mga ito yung mga applications ng quantum, for example, in healthcare, in meteorology, yung mga ganun, yung mga kinds of like high-level applications. And then we have here algorithms to create those or to solve those applications, high-level languages. So for example, if we have Python on classical, we also use Python here, no? Pero different libraries na. For example, yung Qiskit by IBM, ayan. And then frameworks, ayan, circuit models, and compilers, no? Pag-convert ng high level, yung nababasa, readable language into like a circuit model, a circuit, no? Kung gate-based yan. Architecture, the QPU kernel, like kung paano, let's say we have a gate, no? Paano yan i-convert into specific controls, no? Into an actual computer. So nandiyan na rin yung quantum error correction, yan, quantum magic state factors, QRAM, yung sinabi ni Sir Dylan kanina. And then control logic, yan, ito, based na to sa specific modality that we use. No, for example, for neutral atoms, that this is laser based. No, kung superconducting, this is RF based naman. So pulse timing, decoding, no, yung pag-pulse mo dun sa qubit, and then yung pag-read mo as well. Dito yan. Control plane, yan, crosstalk, wiring, pagka-connect ng mga qubits. Ayan, quantum plane, fidelity native gates, connectivity and interconnect, no, qubit to qubit, and then simulator for validation. So, quantum plane, dito na naglalaro yung mga qubits natin talaga. No? Control plane is yung nagko-control, parang patong-patong yung mga yan. And then, balik tayo dito sa architecture. You can see here, quantum error correction. Ayan, as Sir Dylan mentioned kanina, no, we're talking about a very small system. Madaling masira, madaling maalis yung quantum information natin through noise, no? We have thermal noise, yung mga ganong kind of noise, RF noise and such. So that's what we call, ngayon nasa NISQ era, sabi nila. So that's noisy intermediate scale. So noisy dahil maraming noise, intermediate scale dahil kaunti pa lang yung mga qubits natin. So we're playing around 100 to 1,000 qubits pa lang. So may question, what's the minimum number of qubits? It depends on the application. Now, mayroong mga tinatawag na near-term or NISQ era algorithms. No? Pwede na natin silang gamitin using low number of qubits. No? For example, in QML, na yung mga ginagamit sa research right now, no? Pwede nang gamitin. No? And sometimes may advantage naman. No? Pero dun sa bigger gate-based talaga na mga algorithms or yung mga large-scale algorithms, we need millions or 100,000s to millions of qubits. And again, that's the number of qubits. Ibang usapan rin yung noise. No, dapat almost perfect or maganda. No, hindi nawawala yung information natin. So hindi naman natin totally isolate ang system. So we just do error correction, no? Error detection, error mitigation, and error correction. So yan, meron mga bagong techniques dyan na mabigat na research rin yan, mabigat sa math, mabigat sa information theory. Na if you're interested doon, maybe, di ba? Pero yeah, there are companies really specific sa quantum error correction, and it's really important talaga. So what's the use of having 1 million qubits kung agad silang nasisira or agad silang nadidecohere, di ba? So you really need error correction. So where we are today, 2018 pa to, pero we can still say na nasa NISC era pa rin tayo kahit na yan, hopefully we can see the horizon already for fault-tolerant quantum computers. Fault-tolerant, ibig sabihin, mas mabilis makorek yung errors kesa sa nagkaka-errors tayo. No? And that's it. Again, balikan natin yung stack. So we have physical processor, ito yung mga atoms, ito yung mga ions or whatever gamit natin. And then we have the controls, no? Microwave pulses, or in this case, sa superconducting. And then we have the readouts. And then meron tayong layer ng quantum error correction. So we use multiple qubits, physical qubits, for example, 1,000 na mga superconducting qubits to create one logical quantum bit. Ayan. So, yung logical quantum bit na yon, na-apply na yung error correction. And usually, mas mahaba yung fidelity niya, mas mahaba yung coherence time niya. And then, dun sa logical qubits na yon, almost perfect, no? Dun nakapatong yung mga quantum algorithms natin. Ayan. No, yung controls niya, yung readouts niya. No? So, yes, kahit sabihin natin, theoretically, you just need 10,000 qubits. Pero in real life, no, you would need more kasi kailangan mong mag-apply ng error correction. No? So, yeah, sa classical, sa computers natin, sa laptops natin ngayon, hindi na kailangan or minimal lang. Like, it's not really that big of a problem ngayon. No? And sobrang bilis na ng computers. Pero in quantum systems, it's really important. There's a lots of companies working on this. For example, in quantum encryption, the whole stack of it, hardware, software, building the actual quantum computers, iba-iba. Ito quantum cloud computing, and quantum plus AI applications as well. Again, ito naman Europe-based, no? Mga research institutions, hardware-based, no? The processors itself, software investors, and of course users. Now there's actually use cases being done na, for example, with Volkswagen, no? They partnered with, if I remember, Fujitsu, no? They're already using quantum computing to create new materials for batteries, no? So alam naman natin, papunta na tayo sa mga electronic vehicles. No, we need better batteries, we need better materials, so they're already exploring those. No, and Airbus and I think Boeing as well, if hindi ako nagkakamali, no, they're already using that for some of their use cases. This one, programming languages naman. Ayan. So again, yung stack natin, no, and may iba-ibang companies. So of course, kung ikaw yung company, meron kang sariling way kung paano ka mag-interact dun sa device mo, di ba? So for example, IBM, no, meron silang sariling stack, no? We have Qiskit, their full stack library, and then the algorithms nasa Qiskit Aqua, Qiskit Terra, and then yung assembly language nila sa dulo. And then Rigetti, meron din sila, no, iba-iba. Google, meron silang Cirq, no, Cirq library, and then meron silang sariling something of their own on every layer of it. And throughout this lecture series, we'll explore a lot of these. For example, main gagamitin natin is Qiskit. And then for some use cases, we'll use Cirq kasi minsan mas maganda yung visualization nila. Pero overall, it's just the same thing, no? Dito sa baba, as you can see, hardware, no? Kapag nalagay naman yun sa assembly language, no, it's just gates naman. It's just Hadamard gates. It's just Clifford gates or X gates, no? Meron namang X gates lahat ng quantum computers. So you need to convert it. You need to convert from language to language. Pero theoretically, no, you can write one and then you can run your program on any other quantum device. So yeah, I think that's it for that part. Now I will show you it. Shift muna tayo into an actual, like how would you use it? So personally, I use Qubit. Ayan, so ano lang siya, web-based lang siya. It's an IDE. If you use Google Colab, very similar. Ayan, you can just go to qbrave.com. By the way, if we're gonna use this, we will send guides naman. We'll send installation guides or account on how you can create your account. And yeah, kita naman, no? Ayan. Ayan. So, ang kagandahan naman sa Qbrave is lahat ng mga companies na yon, or most of the companies, no, sila na yung nakikipartner with Qbrave para sa atin, isahan na lang yung parang kinakausap natin, or isa na lang yung pinaglalaroan natin, which is Qbrave. No? So, you can just go to account.qbrave.com. Ayan, nakalog in na ako. So, it's still you can still use parang regular VMs here. You have here, yan, mga 2 virtual CPUs. Ayan, and mayroon rin dyan, wait lang. Meron dyan GPUs, mayroong V100 dito. So if you want to use that, and then meron din yung sariling parang plans, you can subscribe if you want. And then, this is also crucial, itong credits na to, these credits is what we use to run quantum jobs. Ayan, so kung mag-access ka ng device, no, like for example, IBM device, no, dito yung gagastusin mo, parang tokens. No? So you can buy tokens dito, magkano ba? Ayan, $10, 1,000 credits. So nakalibre ako, mayroong voucher isang araw. So ayan. So I think kapag gumawa kayong account, meron din kayong voucher agad. Ayan. And then the devices na mayroong access sa Qbrave, really powerful. No? Yan, i-grid view natin para mas ayos. Ayan, so again, pwedeng simulator, pwedeng actual quantum processing unit. For simulators, we have AWS. Yan. By the way, sa AWS, they have their platform called Bracket. Ayan. So ito yung actual na nakakonect sa mga computers, and then nakapatong lang sa Qbrave dyan. No? So Bracket talaga, AWS Bracket. So yung mga yung mga AWS users dyan, very very familiar na. Mag-call ka lang ng API, or you just send a job here. So for example, for simulators, no, mayroong simulator si AWS. We have here a density matrix simulator. We have here tensor network simulator and a state vector simulator. So iba-ibang ways, na iba-ibang iba-ibang applications as well. Sa Qbrave, meron siya sariling simulator. Ayan, you can buy this, or hindi naman buy, pero you can subscribe. Meron naman silang price na $0.075 per minute na paggamit. And then for actual quantum hardware, ayan, you can access them 2 ways, via Amazon Bracket, as I mentioned kanina, and via Qiskit. Ayan, so si IBM, Qiskit diretso, hindi na siya dumadaan ng AWS. And for example, we have here QPUs. For example, here from Oxford Quantum Circuits, or OQC, yung Lucy quantum computer nila is an 8-bit quantum computer. Ayan, and it's gate-based. Ayan, makikita niya may information daan. It's gate-based quantum computer. It's accessed through Bracket, and ito yung kanyang address. Ayan, and then QEra, mamaya balikan natin ang QEra. By the way, yan, hindi sila available right now. Ayan, baka nag-aayos sila or nag-maintenance sila. Rigetti, ito naman superconducting based rin. And 32 qubits sila. Ayan, and gate-based pa rin. Halos gate-based yung mga nandito. IonQ, trap ion. Ayan, ito yung mga pricing nila. 11 qubit quantum computer. Halat ng taga Pampanga 11. And then ito naman yung mas malaki nilang computer. Ito Harmony, 11 qubit. Itong Aria, 25 qubit. No, you can access those. Though ngayon, unavailable siya. IonQ again. Ayan, pangalawang Aria computer. And then Forte computer, Forte 1, 36 qubits. And from IQM, 20 qubits. No? You can mix and match kung ano yung gusto mong gamitin. Superconducting computers from IBM naman, mayroong free access. Although, syempre, i-access rin yan ng mga researchers around the world. So, maghihintay ka talaga na naka-queue, nakapila yung job mo dyan. Saka and all those. And then ito, from Rigetti again, This is their ANCA2 superconducting computer, 84 qubits. Bago lang to. I remember I received like a newsletter no Monday. Kaka-add lang nito. So that's cool. Na bagong quantum computer, you can access it already through Qubit. So all those are gate-based. And then we have here one na analog-based naman. Analog Hamiltonian simulation-based. This is neutral atoms, quantum computer by QERA. Ayan. And ito, HS, yeah. Analog Hamiltonian simulation. And ayan, maybe in the future kapag programming na talaga, we can show you how to program. Pero for example here, kapag nasa lab ka na, mag-launch ka ng lab mo, para lang siyang Google Colab, you just launch your lab, pili ka kung anong VM gagamitin mo, and then, yeah, you can run. And in this example, naka-open na siya. Ayan, parang Jupyter Notebook lang siya. And then, in this case, we're talking about atoms. So itong mga numbered dots na ito, these are actually atoms. So ikaw yung magpo-position ng atoms mo. So very exciting siya. And then, yan, ikaw yung maglalagay-lagay ng atoms. And then, ito, yan, this one is a Kagome lattice. Ayan, so this one is particularly useful for some applications, for example, quantum error correction or yung mga lattices, no? You can do this, no? You can control. Palitan mo lang yung mga coordinates na yan, palitan mo lang yan, no? And there's an actual atom, parang nagmo-move ka ng atom dun sa computer. And then you can also parang control kung ano yung pulses na binibigay dun sa atoms mo. So for example, here, this a waveform, siguro RF signal, ayan, ganyan yung pag rise niya, and then biglang bababa. So yeah, you can design your own. Ito naman parang step-based yung controls niya. And yeah, there's definitely more use cases. Ito, bigla siyang tataas, and then i-hold niya. So yeah, and then you just like call a quantum computer dito sa side na to, no? You can, ayan, available ang QERA, Aquila. So you can send your quantum your circuit dito. And right now we have 256 qubits sa QERA. So yeah, ayan, I think this one was my assignment nung tinuturuan kami. Ayan, and you can represent your problem using a graph. Ayan, connected yung mga yan. And then, kapag isa-solve na niya, ito-try niya i-solve, no? You can iba-ibang solutions. You just pick kung ano yung the best. So for example, ito, yung the best solution is yung pinakamataas na. Yeah, you can represent, again, your problems through graphs. Dito, this is analog, by the way. Analog computing, quantum computing, or Hamiltonian simulation. Pinapakita ko lang kasi in the future, mag-gate-based tayo halos. No? So I just want to show you na there's other paradigms as well for computing. And then for example, ito, no, meron kang 256 qubits. Kung hindi mo naman kailangan yung lahat ng qubits mo, no, like let's say tatlo lang yung kailangan mo per problem, no, edi i-duplicate mo na lang, and then you have like better chances to get the solution. Diba? Ayan. And then, for ano naman, gate-based quantum computation, no, ganyan rin. Ito yung magiging itsura niya, yung circuit diagram. And then you code it, no. This is a matrix, na this is a gate, CCZ gate. No, again, gate-based, ano lang yan, mga linear combination lang ng mga matrices. No, and yeah, ayan, you just define an oracle, you amplify. Yeah, this one is Grover's algorithm, by the way. And then you can start with a classical simulator. For example, ang ginamit niya is an AWS simulator. Ayan, yung support vector simulator niya, SV1. No, pero pwede rin, kung Qiskit based, pwedeng Qiskit Air, yung simulator na gamitin mo. Or pwedeng actual device. So in this case, IonQ yung ginamit niya. And then you can, ayan, sabihin mo lang, IonQ device, yung address niya lang, and then you can send your code, you can send your problem, and then babalik siya sa'yo. So, yeah, quantum jobs, wala akong rinarun na jobs ngayon, so hindi siya nakalitaw. So, yeah, that's QBraid, no, one of the most one of the recently powerful or parang matunog na mga quantum software companies lately. And of course, Colab. You can't go wrong with Colab, Google Colab. No? Pwede kang mag-access directly to AWS. API lang naman yon. No? Pero, I suggest going through QBraid. Medyo mas mahal ng konti, pero the ease of use is better. And then, in the future as well, we'll send you notebooks katulad nito. And play ko lang. Ayan, and then, yeah, we can have like your visualizations na katulad ng ganyan. And then, kapag iba naman yung state na ilalagay natin, ayan, assignment pala ito. Ayan. Pero yeah, ganyan lang. You don't have to install anything unless very specific yung gagawin mo, like CUDA Quantum or QQuantum. You can definitely install this. Mag-pip install Qiskit ka lang. No, that's definitely something you can do. Pero yeah, generally, pwede mo siyang gawin on online IDEs as well. So yeah, although wala tayong physical quantum computer dito sa Pinas, no, it's manageable, and we have lots of developers like you, no, that's already versed on algorithms and such. So maybe we can upskill you guys to become quantum developers as well, diba? And yeah, I think mabigat kasi sa capital yung pagbuo or pag-research ng quantum computers. So medyo matagal pa, kailangan ng maraming investment sa Philippines. So for now, lakasan muna natin yung software capabilities siguro natin para kapag dumating na yung quantum computers here in the Philippines, we're prepared as well. So yeah, I guess that concludes my yapping. Hindi naman yapping, pero yung aking pagdaldal sa inyo about different ways to do quantum computing and different software suites then, di ba? So in the future, we'll send guides kung paano mag-install, kung paano mag-setup ng inyong software development. As long as you have a Google account, yan lang yung kailangan for Google Colab, di ba? So it's a matter of us kung if we want to explore this or not. So there's really not much technical overhead, I would say. So yeah, I think that's it. I will now give the floor back to Vince.
Okay, hi, hello. Okay, thank you, Javis, for your lecture. So let me share my screen. Okay, ayan. So before we officially end the day one of our lecture series, so yeah, if you have questions or concerns or something you want to clarify, so yeah, we still have 10 minutes more, so you can send your questions or clarifications to our Q&A section here in Zoom or through the meeting chat. Okay, so yeah, from Nestor Luna. So yes po, we will send the recording of the session, but yeah, I am not sure if immediately kami makapag-send ng recording, but for sure mag-send po kami ng recording. And also you can access din po yung recording through the Notion site that we sent together with the handbook. Okay, so yeah, I don't see any questions coming. Okay, so okay.
Yeah, I think there's a question. Yung mga platforms po na may subscription, required ba CC kahit mga free tier accounts? Yeah, there's definitely free tier credit card, sorry. Right now sa QBraid, I didn't need to parang may voucher kasi sa Qubit. So you can just claim that voucher and you can like run your code already and get results na. Pero if of course if bibili ka ng ano ng credits and you will subscribe sa plans nila, of course you would need your credit card. Sa ano naman sa Google Colab, as long as you have a Google account, you can run you can open Google Colab. Ang pag-uusapan lang dun is may limits yon syempre. Like, if you want to access like GPU through Google Colab, no, limited siya. I think 1 hour lang every day yung pwede. Tapos T4 GPU yan. I'm not sure if supported yung CUDA Quantum. So if you want yung mga bigger GPUs like mga V100s, no, you definitely need to pay. Pero yeah, for the most part, ayan, T4 is supported daw. That's cool. Pero for the most part, like since we're starting out pa lang naman, smaller simulations, no, we can definitely make do with the simpler um yeah, mga platforms right now. Yeah, you don't need to do T4 GPU pa naman.
All right. Thanks, Jabez, for answering the question. So yeah, okay. I think no questions naman na. But yeah, if you have questions or clarifications after this session, so you can contact us through our social media account or through the email naman. So you can ask your questions there. Okay, so now let's move forward. So yeah, before we officially end the day one of the QNLP lecture series, so first let's have some temperature check. So on a scale of 1 to 10, how was the session? So yeah, send your rating through the chat. Yeah, is it like 1 or seven? Yeah. Okay, there's a lot of like 7, 8, 7, 8. Yeah, I think that's the parang common answer. So yeah, yeah. So yeah, if yeah, I think yeah, probably some information are a bit overwhelming. But yeah, since this session is recorded and yeah, we will also give you copies of the recording. So you can rewatch the sessions, especially for the parts that you think you need to uh rewatch again, especially if there are some clarifications or something that you want to know more regarding that part or regarding that slide that the lecturers presented earlier. Yeah. Okay. So yeah, thank you for answering the temperature check. So okay. So also for the attendance, can Javis, can you send the the attendance link? So for the attendance, the code is 5482. So you need to answer the forms for attendance since it will be part of the or some of the qualifications or requirements for the e-certificate and for the completion of the program. Okay, so again, the code is 5482. So now let's have our photo op. So yeah, requesting everyone to please open your camera so that so we can have our photo op for the first day of our QNLP lecture series. Okay, thanks, Jabez. So again, for the code, the code is 5482 for the attendance, and the link is here naman. So yeah, I'll resend the link na lang. So again, this is the link for, oops. Okay, nasa na yung link? Ay, di ko makopy yung link. Yeah, anyway. So, yeah, again, the code is 5482. So yeah, I think that's all for the day one of our QNLP lecture series. So again, if you have questions or clarifications after this meeting, so you can reach out to us using our social media platforms or through our email. So yeah, again, thank you for attending the day one. Thank you and bye bye.
Thank you. Bye.